everybody hear me okay, by the way?
Yes.
Okay, great.
All right, we have the recording started.
I can hear you perfectly, but the intro breaks up once in a while, and I don't know if it's because of my internet connection or.
It's probably mine. It's my my old computer here is probably struggling under the strain of Zoom. Okay. I have to fan it every now and again. So if you see my hand going like this, it's I've tried to cool down the computer, the laptop. Okay. All right. So I will be quiet, and Venus is going to do the introduction.
Perfect. Thank you. Okay. Well, good afternoon, morning, evening, everyone. It is my absolute honor to introduce Steve King, who's like one of the greatest physicists I've ever known and one of the best mentors I've ever had. He's a world-renowned physicist in neutrino physics, but he's also been doing a lot of other things, grand unified theory, supersymmetry. And if I remember correctly, you told me that for your PhD, you were even doing some QCD stuff. Were you calculating?
That's right. Yeah, I did. That was a long time ago.
Yeah, exactly. Yeah. So he knows everything about everything, if you ask me. And today he's going to tell us about neutrino physics. And please, Steve.
Okay, well, thanks, Venus, for the nice introduction. I'm going to try and share my screen then to see if this works. Right, so I can. Do I share the desktop or just the presentation? I don't know what would be better.
The presentation is usually best.
Right. Okay. Let's go for that then. Okay. All right. So. Let's see. Got to minimize that. Okay. Okay, right. So I'm going to give a sort of gentle introduction to the whole of neutrino physics. So obviously I'm not going to be able to do it justice. I'm going to have to miss out quite a few things, and I'll be superficial to a large extent just to get through the material, but please feel free to ask anything, and I absolutely welcome questions about any, even the smallest thing it's great. So I look forward to your questions. Okay, so here are a few reviews where if you want to know more than I can possibly tell you in an hour or so, these are some reviews. Most of them are by me because I'm familiar with them, but there are the first one is the most up-to-date one, actually. Fruglio and Romanino is the most up-to-date one, but a lot of the material that I'm going to talk about comes from the reviews that I've written, obviously, so you can find more information there. So I'm going to begin with just an overview of neutrinos and what they can do for us. It's a bit like the Romans. What have the Romans ever done for us? Well, neutrinos can do a lot for us in principle. In principle, they can explain the matter-antimatter asymmetry of the universe, the baryon asymmetry. They might have something to say about dark matter. They might even have something to say about dark energy, simply because the coincidence of scales, the neutrino mass is of order 1 electron volt or less than 1 electron volt, and dark energy in some units is a similar scale, and people have speculated about that. There are many implications of neutrinos for particle physics and cosmology. The actual mechanisms for neutrino mass, there are many. Seesaw mechanisms, possibly involving flavor symmetry, extra dimensions. Neutrinos may have something to do with the unification of matter and forces and flavor, may be related to supersymmetry, grand unified theories. In fact, some grand unified theories predict neutrino mass, such as SO10. We've already mentioned baryon asymmetry of the universe, dark matter, and dark energy. Inflation, neutrinos with supersymmetry at least could give a candidate for the inflaton, namely the right-handed neutrino. So there's a whole lot of cosmological implications as well as particle physics implications of related to neutrinos and neutrino mass. So let's just think about the nature of neutrino mass and mixing, and just think about just a general qualitative overview to begin with. So to begin with, neutrinos have tiny masses, much, much less than the electron mass. They mix a whole lot, which is quite unlike the quarks. And they introduce into the standard model another 9 parameters, namely 3 masses, 3 angles, and 3 phases. So the parameter count on the standard model, which used to be 19 or 20, or depending on how you count. So now we've got another 9 parameters. So now the parameter count is getting on up to 30 for the standard model, which is rather a lot of parameters for a fundamental theory. And the other thing to say is that the origin of neutrino mass and mixing is unknown. So everything I'm going to tell you about, theoretically at least, is untested, hypothetical, and speculative. So it's experimentally, we just don't know what the origin of neutrino mass and mixing is. We know it's there, but we don't know the reason for it. Okay, so first question is, how do neutrinos fit into the standard model? And well, here's the standard model in Lego building blocks. I've divided the quarks and leptons into left-handed and right-handed ones. And for the left-handed ones, I've shown how they transform under SU3 color and SU2 left. So you can see that the quarks are glued together here into SU3 triplets, and the leptons are singlets of SU3. And the left-handed quarks and leptons are doublets. So you see the neutrinos appear here as the upper half of the doublets. For the right-handed ones, well, the quarks are still triplets of SU3 color, but now they're no longer doublets of SU2. Instead, they're distinguished by hypercharge, U1 hypercharge. So you can see the distinguishing hypercharges plotted here. And I've introduced right-handed neutrinos. So this is an addition to the standard model. And these right-handed neutrinos can help us to understand the origin of neutrino mass. You don't have to have them, but if they're there, they open up many new possibilities for neutrino mass. Okay, this is just a diagram for what I mean by left-handed and right-handed, but I think everybody knows that. Okay, now neutrino oscillations. These, the first thing to say about neutrino oscillations is that this is only possible if neutrinos have mass. So observing the phenomenon of neutrino oscillations is a kind of proof that neutrinos have mass. So this history of neutrino oscillations goes back to 1968, motivated by the solar neutrino problem by Pontecorvo and Gribov. And the basic idea is that neutrinos are quantum superpositions of mass states. So for a two-state system, you have nu1 and nu2, and the weak states are nu-e and nu-mu, and they're not the same as the mass states. And that simple phenomenon gives rise to different propagation speeds for the different mass components. So if you produce an electron neutrino, it has two different mass states, so you get 2 different propagation speeds, and that leads to this phenomenon of neutrino oscillations. So here I'm plotting probability of the electron neutrino going to a muon neutrino, and you can see that it oscillates up and down according to this formula here. So this is a simple formula. You might remember that. You might try and remember this because we're going to come back to it in a few slides' time. So it goes like sine squared 2 theta, theta being the same angle as this one here. It determines, it parameterizes the different mass eigenstates in a weak eigenstate. And then it's sine squared, delta m squared is the mass squared difference of the two nu1 and nu2 neutrino masses. L is the length that they travel and E is the energy. So this is plotting, this particular formula will be for fixed energy, plotting against L, probability against L. Okay. Right, so an object of great interest is the lepton mixing matrix named after these people here. So it's called PMNS, lepton mixing matrix. And it's the matrix that relates the standard model states, so the neutrinos which appear in the upper components of the doublets in the basis in which the charged leptons are the mass eigenstate charged leptons. So that's the definition of nu e, nu mu, nu tau. And nu1, nu2, nu3 are the three mass eigenstates. So I'm just generalizing what we had on the previous slide to three neutrinos, because we have three families. So this is the 3 by 3 generalization. And this nu1, nu2, nu3, they correspond to these mass eigenstates. I'll come back to this diagram in a moment. You'll see a bigger version of this as we go. Okay, so that's the lepton mixing matrix in generality. You can parameterize it in various ways, but the particle data group tells us how to parameterize it. So we have to parameterize it this way as a product of these matrices here, a theta 2, 3 subblock, a theta 1, 3 outer block, a theta 1, 2 upper 1, 2 block, and some phases, Majorana phases. So these are known for historical reasons as atmospheric angle, reactor angle, solar angle, and Majorana phases. When you multiply these three matrices together, you get this kind of purple matrix here, together with these Majorana phases. And this purple matrix is actually identical in form. It's parametrically identical to the quark, the CKM mixing matrix, except for the leptons, these are brand new parameters, so they're different mixing angles from the quark sector. Okay, so here's the 6 parameters which are measurable in neutrino oscillation experiments. And I'm assuming 3 active neutrinos throughout the talk. There's some ongoing speculation that there might be extra light neutrino states called sterile neutrinos. So you can have a 4th neutrino or maybe a 5th, maybe more. But there's no evidence for those, no experimental evidence for those states at all. So throughout the talk, I'm going to just stick to the minimal 3 active neutrino paradigm. So within that paradigm,
just to clarify, Steve, isn't there cosmological evidence against those?
Yes.
Those ones? Okay.
Yes, there is, in fact, yeah. So you have to do something pretty special if you want a 4th light neutrino, because as you say, the number of effective neutrino species is close to 3. So yeah, you have to do something cosmologically non-standard if you're going to have a 4th sterile neutrino. That's absolutely right. Yeah.
Can I ask Steve just the difference between active and sterile? In the picture you had of the standard model, you had the 3 new right-handed neutrinos. Are they active in the sense? Are they supposed to have hypercharge? Is that why they're active?
Right. Yeah. Excellent. Thank you, Brian. That's a very good point. These are okay. So I've just contradicted myself because these are actually sterile neutrinos. So they don't carry any quantum numbers at all. They carry 0 hypercharge, although you can't see it on this the way I've plotted them, but they carry 0 hypercharge actually. So they are actually sterile neutrinos. But I'm going to be assuming that these exist at higher masses. So well above 1 electron volt. So in fact, they might even be as heavy as the grand unification scale, these objects. So so it's a bit of, there's a bit of a ambiguity in nomenclature about this. Technically, they are sterile neutrinos, but then they play no role in low energy neutrino physics. If they're heavier than, if they're much heavier than 1 electron volt, they play no role in neutrino physics, or really, well, they play an indirect role in cosmology in terms of leptogenesis.
Even though they have no gauge charges, they could have Yukawa coupling.
They do,
So they
could, and they will in general have Yukawa coupling. So they're not sterile in the sense of having no interactions. That's right. They do have interactions.
Technically, people would still call these sterile, would they? Is that the terminology?
So there's a bit of a split what people call them. Some people would call them right-handed neutrinos. Some people would call them heavy sterile neutrinos. Some people call them different things. But when I said I'm going to stick to the 3 active neutrino paradigm, I'm talking, I guess I have in mind an effective field theory point of view. So once these things, if these things are very heavy, you can integrate them out of the theory, and then we're just left with the 3 light active neutrinos. So yeah, so we have to be careful about the nomenclature. But
so,
yes,
so there is an ambiguity in the way people describe it. Because I often get confused when people talk about activist.
No, you're absolutely right. People talk about them in different ways. So some people will call these sterile neutrinos, and some people call them right-handed neutrinos. But the key thing to be aware of is whether those neutrinos are playing any role in neutrino oscillations or not.
And that's determined by the mass.
That's determined by the mass. So if they're much heavier than 1 electron volt, then they're not going to be playing any role in neutrino oscillation experiments.
So when you say you think of it as an effective field theory where you can integrate out these heavy guys, you just mean 1 electron volt, right?
Yeah, so by the time you get down to 1 electron volt, these things are not going to be present in your effective theory in a normalizable sense.
Yeah.
Okay. All right. So here's the assuming 3 active neutrinos. Then here's the parameters. You've got the delta M31 squared, the delta M21 squared. The definition of these deltas, remind you, is just the difference in the mass, in the squared masses. The atmospheric angle, theta 2, 3, the Stoller angle, theta 1, 2, and the reactor angle, theta 1, 3, and also the CP violating phase, delta. So all of these are accessible and measurable in neutrino oscillation experiments. Okay, so let's just go through them then. Here's the 2 mass square differences. Here's the blow-up version of the diagram that we had before. You can see that you've got 3 mass eigenstates. Well, I'm plotting mass squareds here, so it's M3 squared, M2 squared, and M1 squared. And the mass square differences are just given by these arrows. So this is the atmospheric mass square difference, the solar mass square difference. A couple of things to point out, or 3 things probably to point out. First, the baseline, the lowest neutrino mass is unknown. So we know it has to be less than some number, certainly less than 1 electron volt. But the actual value is not really known. There's an ambiguity whether the heaviest one is, whether the pattern of neutrino mass is as in the left-hand panel or in the right-hand panel. And the meanings of the different panels are that each mass eigenstate has a probability of containing an electron neutrino, a muon neutrino, and a tau neutrino given by the lengths of these colored bands. So this particular mass eigenstate here has approximately 50% chance of containing a muon neutrino and 50% tau neutrino with a tiny probability of containing an electron neutrino. So that's the meaning of these colored bands. This one here is roughly a three-way split. And you see this one here is roughly a three-way split. So the composition of these bands is fixed, but the ordering of the bands is not fixed. It may be that this mass eigenstate, which is a third, a third, a third, this actually could be the heaviest one. And from an experimental point of view, we don't know. All we know is these mass squared differences here are the differences between these different mass squareds. These are known, but the ordering of the mass squared differences is still ambiguous. Okay, here's the three mixing angles. If you ignore the CP phases, then these are just like Euler angles, which relate the mass eigenstates nu1, nu2, nu3 to the weak eigenstates nu-e, nu-mu, nu-tau. And this is a sort of pictorial understanding of what these angles are.
I'm sorry, Steve, do you mind going back a little bit? So, so actually on the previous slide, I noticed you didn't say anything about the Majorana angle, the delta
Excellent.
1, 2.
Excellent, yeah.
Okay, so
Very
is that
good.
going to come later?
Very good. It will come later. It will come later. But you make a very good point that neutrino oscillations are not sensitive to the Majorana phases.
Mm-hmm.
So they're only sensitive to one phase, which is this delta phase. They're not sensitive to Majorana phases. That's right.
Okay.
So it doesn't matter how accurate your neutrino oscillation experiment is, it will never give you information about the Majorana phase.
Okay.
Phases.
Yeah. And on the next slide, this is probably a very, very stupid question, but why are these two our only options? I mean,
no, it's a good question, Venus. It's because experimentally the ordering has been determined in terms of the solar ordering. So by looking at solar neutrino oscillation data, that ordering is fixed. So this a third band is always heavier than the lighter one. So there's no ambiguity there. So the only ambiguity actually is in the atmospheric ordering, whether keeping the ordering of those two bands fixed. The only ambiguity is whether this 50-50 band is the heaviest one or the lightest one. That's the only ambiguity. Yeah.
Perfect. Thank you.
Okay.
And I also asked Steve, while you're on that transparency, the question mark at the bottom. I mean, I know you can't get that from neutrino oscillations, but you can get a handle on it from cosmological.
Absolutely right, Brian. Absolutely right.
That's where this 1 electron volts come from, is it?
That's where the 1 electron volt comes from. Yeah, it's actually less than 1 electron volt, but it comes from CMB and galaxy structure formation. So it's but we'll come onto that. It's some fraction of an electron volt, 0.23 or something electron volts. Yeah.
What are the two columns you have written, left and right?
Sorry, say again.
You have two columns here for the masses. What are they?
These two panels are two alternative orderings for the pattern of neutrino mass. So the one on the left, actually these are given names. Thanks for asking, because these are given names which I didn't mention here. But the one on the left is called the normal ordering, and the one on the right is called the inverted ordering. But a priori, there's nothing normal about this or abnormal about this. They're just two. So these are historical reasons they're called normal and inverted. But that's what they're called. Yeah. So the one on the left is called normal ordering. The one on the right is called inverted ordering.
And how does it show up in CMB? How does it affect neutrinos affect CMB?
So the CMB is only sensitive to the sum of neutrino masses. So that the sum of, because the mass squared differences are fixed, the sum of neutrino masses only depends on the mass of the lightest, the mass scale, in other words, the mass of the lightest state. So that's the only one that's not fixed. And that's the one that you can get a handle on by from the CMB.
But how does it show up in CMB from the spectrum?
Oh, I see. Okay. So you know, you've got this wiggly line in CMB, the angular power spectrum. And you can model that angular power spectrum with various assumptions about neutrino masses, whether they're massless or whether they have masses. And by trying to fit that data, you can get a limit on the neutrino mass.
Okay.
Actually, looking at the diagram there, Stephen, I don't think inverted is very good terminology. It looks to me more like a cyclic permutation.
Absolutely, absolutely. The notation's terrible. I mean, yeah, I've no idea why one should be normal and one should be, but yes, in normal and cyclic would be even better. Yeah, good.
I'm sorry, I missed the how you got the fractions of the different colors.
So these fractions come about through the
We can't hear you.
I thought it was me.
We can't hear.
Your sound seems to be gone, Steve.
Nothing here.
Hello, can you hear me?
Yes, again,
Okay.
yeah. Okay.
Yeah, I just unplugged my headphones and plugged them back in again. Maybe I've got a loose connection. Yeah, so if you look at this, if you look at this formula here, you've got the weak states are given by a matrix. This is a matrix multiplied by a column vector nu1 and nu2. So you can take the inverse of that matrix and then express nu1 and nu2 as the inverse matrix times nu e and nu mu column vector. So those elements of that matrix would give you the amplitude of a mass eigenstate nu1 containing nu e and nu mu. And if you square those amplitudes, that would give you the probability of a particular mass eigenstate containing some amount of nu e and some amount of nu mu. So that's what's going on. I mean, this is a 3x3 version of it. Okay.
May I ask a question on this slide?
Mm-hmm.
Now, this is really a stupid question, but you said the way we define nu, e, mu, and tau is basically the gauge eigenstate, but after we have already rotated the e, mu, and tau into the mass basis.
Right.
Why is that? I mean, is there a historical reason for it?
Yeah, well, there's a physical reason for it, because when you make a neutrino beam of neutrinos, then they tend to come from like the decay of a muon. So a muon neutrino would come from the decay of a muon, and so physically you start with the mass eigenstate muon, and that decays into some neutrino which we call nu mu. So it's determined by physics, really. And the ultimate reason is that the charged lepton masses are much heavier than the neutrino masses. So that's why physically it makes sense to do that.
Yeah, because I mean, this is something that's always confused me, because we don't do that with the quarks. You don't rotate. Yeah, you don't rotate the bottom type ones into the mass bases.
Absolutely, yeah, and it's because the quarks have similar masses. Mm-hmm. But in this case, because the charged leptons are much heavier, then it's convenient to define these. But we later on we'll give a more general definition as well. But okay, so.
And if I understand correctly, you're saying that some angles are 1/3. Is that what's going on with the three colors?
Right.
Okay.
Absolutely. So if you look at this, you see that this particular mass eigenstate is about a third, roughly, of electron, muon, and tau neutrinos, and that, well, we will discuss the implications of that a bit later. Yeah. But yes, basically, it means that these elements of the PMNS matrix are equal. This column of the PMNS matrix are going to have equal elements. Actually, that's called tri-maximal mixing, that case. And this equal amounts of green and blue here, this is called bimaximal mixing. So that's why some people call this pattern tri-bimaximal mixing, because you've got tri-maximal mixing for one mass eigenstate and bimaximal mixing for another mass eigenstate. So you may have heard this terminology, tri-bimaximal mixing. So that's the reason for it. And we're going to come on to that too. Okay, and I think we're down to the one remaining oscillation phase. So this is delta. This is the one that you can measure in neutrino experiments. Actually, could I just take a brief pause here? I just need to go to the loo for a minute. I should have done this earlier, but
no problem. Of course you can. Yeah.
Okay, I'll be back in a second.
Yeah.
Yes, Steve has realized with the number of questions that we asked that this is going to go on for more than an hour.
Well, we tend to, we have drawn on for more than 2 hours on occasion. So
I know. Yeah,
I try to warn our speaker.
Yeah.
The advantage is that it's recorded, so if anyone really has to leave, they can come back to it. And it's our only chance to ask these questions. So we
absolutely, yeah.
So we are relaxed about letting the time run on.
Absolutely, yeah. I mean, it is absolutely fantastic. I know in Southampton they do something really nice that before any seminar, there's a 15 minutes start for just the PhD students. No postdocs or supervisors are allowed. So the speaker kind of gives a very brief introduction to what they're going to be talking about, and the students can ask whatever question that they want in case they don't feel comfortable asking it in front of their supervisors. Which is quite nice, but
yeah, they do the same in Heriot Watt. They actually have a 2-hour session, and the first hour is for PhDs and maybe postdocs as well, and that's kind of elementary introduction, and then the seminar afterwards.
That's really good. Yeah.
That's probably something better done in person. It's very hard to ask someone.
Oh, absolutely, yeah.
Yes. Yeah.
Okay.
Okay, thanks. All right.
We are likely to keep you a while, so it's a good idea to take a break.
Yeah, I realized we might go over time, so
yeah.
Okay, great. So that's the oscillation phase. Right, so now a little bit of history. So neutrino oscillations were definitely discovered in 1998. There were some hints before that time, but they were conclusively discovered by Super Cameo Candy in 1998, which was this detector that looked for neutrinos coming from cosmic rays, and they could tell the direction of the neutrinos that were coming straight down from the upper atmosphere to the ones passing all the way through the Earth. So the Earth is not playing much of a role here. It's the point is it has a different baseline. Remember this L in that formula here, this L here. So this is a long L because it's traveling further, and this is a short L because it's coming from above. Basically, the upper atmosphere is like a spherical source of neutrinos because of the impact of cosmic rays producing neutrinos. And this is some of their data here. And what's actually plotted is data divided by prediction. So one is where you have no neutrino oscillation, and you see for the short L over E. So here the neutrinos coming from above, they don't have enough distance to oscillate, but the neutrinos that travel further, they oscillate. So if you plot the data over prediction, it follows this curve here, and this, believe it or not, this curve here looks a little bit like this formula, sine squared delta m squared L over E. It's just that it's on a log scale, so it doesn't look very much like it, but it obeys this formula quite well. So that was the first evidence for neutrino oscillations. And since then, there was a kind of mini explosion of data. And this is a brief history from 1998 to 2012. I'm not going to go through this in great detail, but you can see the main thing is every couple of years, something was measured. So the first Super Kamiokande measured this theta 2.3 in 1998, then theta 1.2 was measured in solar neutrino experiments in 2002. These little medals mean that the experiments won the Nobel Prize. And then again, 2002, the electron neutrinos were shown to convert to a linear combination of nu mu and nu tau, for reasons which I'm not going to go into. 2004, so all of above is to do with neutrinos coming from the sun, that's solar neutrinos, or neutrinos coming from cosmic rays, that's atmospheric neutrinos. But actually the phenomenon we're looking at is nothing really intimately related to cosmology or astrophysics. It's really about the properties of neutrinos. And this was proved by experiments on Earth from a nuclear reactor, which saw the same effect. So beams of neutrinos, not beams, but neutrinos coming from nuclear reactors were shown to disappear and reappear in experiments a couple of years later. And then beams of neutrinos were made a couple of years after that. Beams from accelerators, so muon neutrinos from accelerators were shown to disappear. And later on, they were shown to convert to tau neutrinos by this OPERA experiment. This is the same experiment, by the way, that wrongly claimed they'd seen faster than light neutrinos, which was discredited. But what it did see, and the solid result of the OPERA experiment was they saw tau neutrinos, which simultaneously discovered this oscillation nu mu to nu tau. It simultaneously discovered the tau neutrino itself and the oscillation. And then the first hint of theta 1.3 was in 2011 by this experiment T to K. And then the definitive measurement was made of theta 1.3, the one remaining angle was made in 2012 by Diabé, Reno, and Double Show. And I'm firing these experiments at you, but I'm going to show you some pictures of them now. Well, this is the Nobel Prize, which was awarded in 2015 for the discovery of neutrino oscillations and neutrino mass. Here's some of those experiments that I've been talking about. These are the reactor experiments, Diabé. This is a map of where they are. This is in China, Double Show in France, Reno in South Korea. Here's the detectors. And Diabé is no more. That's been decommissioned. But now we have a new experiment in China called Juno, which is coming soon. And you can see where it is. This is a map of South China. And you can see it's in this little square here. And here's the Juno experiment. It's situated about 50 kilometers away from these two reactors. And that's the picture of the experiment. A little bit about neutrino oscillations. This is a little bit technical, but I'm not going to be too bothered. The formulas are actually pretty complicated. Remember that sine squared 2 theta with sine squared delta m squared L over E. That's the two oscillation formula. When you generalize that to 3 neutrino states, things get rather complicated, especially when you include the phase as well. So it leads to these rather complicated oscillation formulas. This is for nu E to nu E, or nu E bar to nu E bar. So this is electron neutrino oscillation. So you can plot the probability against L over E here. This is electron appearance, sorry, disappearance. So you start with electron neutrinos from the reactor, and then they disappear, they reappear, they disappear. Okay, so they look like that. This is over a scale given L over E of roughly of order 1,000 to 4,000 kilometers per GeV. And Diabay and Reno, they sit here around this point here. So the parameters are chosen so that they sit around there. But the Juno one, the new one that's coming in, that's going to be sitting much further out. So that's at 50 kilometers. These experiments have their neutrino detectors close to the nuclear reactor, 2 kilometers. These are 50 kilometers away, much further away. And so they're seeing different features of the oscillations. The panel on the right is the same as the panel on the left, but just extended to larger distance scales. I don't know if you can imagine that. This goes out to 4,000. So the first panel on the left is only going out to here. So these wiggles you see are just the first few wiggles. But if you zoom out, you see this thing starting to go down, and in fact it goes down. It wiggles, but the envelope of the wiggles also oscillates as well. It's because of this complicated formula. So it looks like this. And these two blue and red oscillations look like this on a larger scale.
So with Juno, they keep the source, but they just dig a new, I guess, tunnel for the target, right?
Exactly. Yeah,
and
exactly.
The reason the plot goes all to 35,000 is because hopefully there's plans for a new detector at some point in the future.
No, that's just there's no. I could have stopped it here because Juno is going to sit at this point. Sit at this point here.
And what is the advantage? Precision, is that the only advantage?
Well, the advantage of being much further out is that you can measure parameters such as delta m squared 2,1, which you wouldn't be sensitive to that if you were here, but you are sensitive to delta m squared 2,1 here, because the minimum of this actually is determined by delta m squared 2,1. So the envelope of this, which is what you're looking at. So that gives you a handle on delta m squared 2,1, which you wouldn't get here. You only get a handle on delta m squared 3,1, which you already know actually from other experiments. So this gives you a new handle on delta m squared 2,1, and also the solar angle as well that goes with it. So delta m squared, sine squared 2 theta 1 2. So this term here. So you get a nice handle on that term there, which you wouldn't get from this experiment. So you can get high precision measurements of theta 1 2 and this delta 2 1.
Okay, so they had those two terms, delta 1 and delta 2 1 is assumed to be is effectively 0 in the earlier experiment.
Right.
Okay.
Exactly.
But I thought, I mean, theta 1,3 was the, I assume, most difficult one that they had only measured more recently.
Well, this is the theta, the theta 1,3, right?
Yeah.
Right. If you're interested, in theta 1,3, then this is the term to look at, because this term is controlled by theta 1,3. So if you set theta 1,3 to 0, this kills this term completely. So over here, you're really, by looking at electron disappearance, you're really getting a high precision measurement of theta 1,3, because that's controlled by this.
Yeah, but yeah, I mean, from the list of experiments that you showed, theta 1,3 was coming quite far at the bottom, and it seemed like theta 1,2 was one of the first angles that they measured.
Right.
So I guess there are probably then other experiments.
Yeah, that's right.
Okay.
So yeah, in fact,
because Juno seems to be the perfect one for measuring theta 1,2.
Yes, exactly.
Yes.
Exactly right. Exactly right. And Diabay is the perfect one for measuring theta 1,3. So these reactor experiments were only done pretty late in the day, really. If you look at, you see these reactor experiments were done, these high precision ones were only done in 2012. So in the early days, well, the very first one was Super K.
Yeah.
But yeah, once they started to do these reactor, well, Camland actually was but it didn't have the precision of Diobey. So these are the experiments that enabled Theta 1-3.
So the Theta 1-2 that we measured from, I guess, solar neutrinos.
Right.
Yeah.
Exactly.
So is the precision not good enough, or we're just kind of, it's a sanity check to look it up with Juno?
That's a great question. Yeah. So it's very good, actually. You get very good precision from solar neutrinos, but you can get better precision from the reactor, from the other one. So people are always striving for higher precision. And you can ask yourself why do people want higher precision? Well, that's the theoretical question which goes to the heart of the origin of neutrino mass and mixing. You want to compare your models to your model predictions to the data.
Yeah, I mean, it wouldn't take me much to be convinced that we should measure it. I guess politicians who have to fund it. That would be much harder.
Right. But
But yeah, thank you.
Right. Okay. Right. So just completing our survey of experiments. Then this is Theta K. This was one of the accelerator neutrino experiments in Japan. This is actually firing beams of neutrinos from an accelerator complex, which is depicted here, to actually to Super Kamiokande. Used the same detector that discovered neutrino oscillations coming from cosmic rays can also be used to detect neutrinos coming from the beam of neutrinos. So you can use Super Kamiokande in two different ways. And here you're using Super Kamiokande to detect neutrino beams coming from this accelerator complex. J-Park, it's called. Yeah. And there was an earlier experiment as well at the KUK laboratory, another accelerator in Japan, which also directed its beams towards Super Kamiokande. Okay, and then muon neutrino oscillations is another one. So this is the formula that's relevant for the old Super Kamiokande experiment, which basically can study muon neutrinos to muon neutrinos, or the disappearance of muon neutrinos depends on this term here. So you start with muon neutrinos, they disappear, then they reappear and they disappear. And instead you get tau neutrinos. Okay. And then finally, we've got electron neutrino appearance. This is when muon neutrinos convert to electron neutrinos. Please don't worry about these formulas. They're incredibly complicated, but the key thing is what I've circled here, which is this particular one is sensitive to the CP phase. So if you're wondering how can oscillation experiments get a handle on the phase delta, it's because of this process, nu mu to nu e, because the complicated formula has a dependence on delta CP phase. So that's the take-home message of this slide is that this process here depends on the CP phase. The details we don't need to worry about.
Sorry, Steve, do you mind going back one slide?
No.
Here. So why does the muon neutrino to muon neutrino oscillation only depend on Theta 2-3? I mean, wouldn't it at some point also turn into the electron neutrino?
Exactly right, Venus. Yeah, exactly right. So this statement is only true to leading order. So I've neglected these terms here. Okay. So the terms where it converts to an electron neutrino depend on this ratio of delta m squareds, which is a very small number. So you can do some kind of expansion in this small. So yeah, I've neglected those terms. Right.
Thank you.
Sure. Okay, so looking to the future then, here's a couple of future long baseline, LBL is long baseline experiments. There's one in the US, which is going to fire a beam of neutrinos from Fermilab to this lab here, which is actually Sanford Underground Research Facility, which is some extension to some existing underground experiments. So this is some distance of 800 miles. So a very long baseline. And then Japan have also, so this has been funded. This will go ahead, June. It will start, I was looking on the webpage today, they claim it will have beams by 2026. So not too far away. And then you've got the Japanese competing experiment, which is hyper Kamiokande, which has these very large water Cherenkov detectors, just like super Kamiokande, but this is like a super Kamiokande, much larger tanks of water than super Kamiokande.
Question again.
Okay.
Sorry, I have another question.
Sure.
So what is that weird bump on the dune experiment? I'm guessing it's a mountain.
So the scale of this is not to scale Venus. These are all very close, like within 1 kilometer of Fermilab. So this is within the Fermilab grounds, whereas this is 800 miles. So this is confusing and misleading. It's not to scale. So this is just showing that you have to point the neutrinos downwards. So in order to reach a target 800 miles away, you can't just point the neutrinos horizontally. You have to point them down into the Earth. So I think that's what this is emphasizing.
I see. Okay, yeah, because it looks like then actually the neutrino production is happening far away from Fermilab, but
Right.
I mean, unless the Earth is flat, then
So these, exactly. So the distance between here and here is only about 1 kilometer. The distance between here and here is 1,300 kilometers. So this is I agree. This is a misleading picture. But I guess they just wanted to emphasize that there was a detector here. This is called the near detector, and this is called a far detector. And the technology is different as well. These detectors are made of liquid scintillator, whereas these detectors have water in them, so it's quite different.
Is there a reason why they're different?
Yes. It's to do with the energies and precisions. Well, basically the energies of the beams and the width of the beams. So that's kind of depicted on these graphs here. You see the two very different baselines. The Dune one is called a wide band beam, which is basically you have quite a spread of muon neutrino. Remember, from accelerators, you're producing muon neutrinos from pion decay. So these have a spread of a few GeVs, whereas the T to HK, hyper K beams are much narrower. It's a different scale here. This is 0.4 to 0.8, so sort of half a GeV. So this is called narrow band beam. This is called wide band beam, and the technologies somehow reflect the nature of the beams. Beyond that, I don't really know. I'm not an experimentalist.
No, that was perfect. Yeah, that's all I needed to know.
Yeah. Okay, and this is what the future will look like. You'll be able to plot from these experiments. You'll be able to plot sine squared 2 theta 2 3 against delta. So at the moment we don't really know the phase, but in the future we can know it. We're going to be able to know it quite accurately. So these the big selling feature of these future experiments is that they will measure the CP violation. It's quite a big deal. Okay, and this is just summary of the parameters and how we know about them, which we've said that. This is the
Sorry.
latest.
Steve, do you mind going back again? One more slide.
No.
So what does this mean for the CP violating angle to move between 0 and 100? I mean,
Oh, well, since we don't know where we are on this plane.
Yeah.
So these black dots are sort of random points where we could be, and if having chosen this black dot, these are the uncertainties with which we could measure delta and sine squared theta 2, 3.
But what is the difference between the 3 black dots on the sine theta 2, 3 squared 0.5?
Because we don't know what delta is at all. Delta could be anywhere along here.
Yeah.
So if all this is saying is if delta were 90 degrees.
Oh, those are degrees. I see. Okay. Yeah.
Yeah. If delta were 90 degrees, this would be the error we could measure delta. If delta was 0, this would be the error we could measure it. So you see the error depends on the actual value, and we don't know what these values are. So we've just thrown these kind of darts.
Yeah.
Or well, they're not darts, but they're actually benchmark points. So these benchmark points are plus 90, these are minus 90, and these are 0. But
so there is absolutely no knowledge of what delta is.
Well, there is, yeah. On the next slide, on the next slide, we will see actually what this one. We will see what we know at the moment. So this is what we know. This is everything we know as of now. So this is a global fit to all the data, all the oscillation data. And you can see that normal ordering is preferred over inverted ordering by a delta chi squared of 7.
Wow.
Okay, so it's 2 sigma, or 2 point something sigma, 2.5 sigma preference for normal ordering over inverted. So the best fit value of delta is 230. It looks like quite a small error for something that we don't know. But if you ask what is the 3 sigma range, it can be anywhere in this region here, 144 to 350. So it has a very large uncertainty. And remember that this is an indirect inference of what delta is, because there's no experiment that's by itself that's sufficiently accurate to give any information on delta. So this is a global fit of all the delta, of all the data. So this is a summary of what we know so far. Okay. Right, so that's what we know, and this is what we don't know. This is experimental open questions. So this is what the PMNS matrix looks like, roughly. This is a cartoon. So you see the equal states here. The nu 2 state has roughly equal amounts of nu e, nu mu, nu tau. The nu 3 state is 50-50 nu mu, nu tau. These correspond to these colored bands we had before, although the color coding is different now. And this is nu 1. So this is what we know about the PMNS matrix, this modulus of the elements squared actually here. This is what we don't know. We don't know the octant degeneracy. In other words, we don't know whether theta 2, 3 is less than 45 or greater than 45. We don't know the mass ordering. Let's go around this way. We don't know the mass ordering, well, normal or inverted. That's what we talked about before, those 2 panels. And we don't know CP violation, which actually plays important roles in these elements here. So these are the things that we don't know and which were going to be targeted by the future neutrino experiments. Theory of neutrino mixing matrices. I think I'm going to just flash this because everybody knows this from quarks. Because of the standard model, we know you have Yukawa matrices, you diagonalize them, and then you look at the charged currents. And the CKM matrix is the matrix that relates the W couplings of the up charm and top mass eigenstate to the downstrange and bottom. Well, you can do the same thing in the lepton sector. This is a formal definition of the PMNS matrix. You're looking at charged currents connecting E mu and tau to nu 1, nu 2, nu 3. This is nothing more than what we've already shown, except that now I'm starting from a Lagrangian. here, but otherwise it's the same. Right, so it's interesting to compare CKM matrix, which is dominated by the diagonal elements. In fact, it's almost the unit matrix, apart from Cabebo mixing here, and then some smaller elements here. This is a cartoon of CKM. This is a similar cartoon of PMNS. So here we see the tri-maximal mixing, these elements equal, and the bi-maximal mixing here. So very, very different. And one of the theoretical questions is why are they so different? Now I'm going to get on to
in your cartoon, you have one of them being 0. Is it actually known to be 0 in the upper right-hand corner there?
That's right there. So that one is definitely not 0. That one depends on the θ13. So if we go back to the actual non-cartoon version here, this is the non-cartoon version. You can see that that element is θ13. So that's definitely non-zero.
But it's unknown what it is. Is that why you've left it blank?
No, I've just left it blank.
Oh.
I should have put a little dot in there. It's actually very accurately known. θ13 is very, very accurately known.
Okay, and it's a small dot.
Yeah.
Okay.
Yeah. I should have put it in. It's here. You see, it's actually one of the most accurately known ones. It's 8.62 degrees plus or minus 0.12. So it's one of the more accurately known ones. Yeah.
Thank
so
you.
yeah, so that dot should be there for sure. Okay, so now I've just realized that I've been speaking for an hour and I'm only about 1/3 of the way through my talk. So I don't know what to do. Should I?
Well, we have the time.
Yes.
Yeah,
Is
these
that
seminars
true?
usually go on for 3 hours. Yeah,
Is that right?
Just keep going, Steve.
absolutely. Yeah.
Yes, if you need another break at any time, just please.
Is that okay for me
Yeah.
to just to keep
Oh,
going?
absolutely. Yeah.
Absolutely okay.
This is wonderful.
I know. Yeah.
I've
Like-
never. It's been I don't think I've ever been to a place. I mean, given a talk where I've not been under time pressure. This is fantastic.
I know. It is brilliant. Because
Okay.
I mean, as when you were taking a break, we were talking about how wonderful it is in Southampton that they have 15 minutes for the students before the actual seminar. But yeah, this is even better. We're just
That's
here
great.
to learn physics.
Fantastic. Okay. So now I'm sort of edging towards some theory now. So one old proposal was something called the problem is to try and understand this pattern, including this entry here. So one old idea was called mu-tau symmetry. Maybe there is a discrete symmetry, permutation symmetry, a Z2 or something, permutation symmetry, which will relate muon and tau electrons. And the basic idea is that these two rows are the same. We don't say anything about the top row of the PMNS matrix, but the lower two rows have equal magnitudes. And the consequence of that is that the θ13 would be undetermined. We don't know what that entry is. That's the θ13 entry. But if these two rows are equal, then that would be bimaximal mixing. So this θ23 would be 45 degrees. And also the CP phase would be 90 degrees, it turns out. If you constrain the two rows to have equal magnitudes, that actually constrains the CP phase to be 90 degrees. You can see that by actually studying the parameterization, the full PMNS matrix parameterization. You can convince yourself that this has to be 90 degrees. Although I've written this as 2008, this idea actually goes back to 2002, Harrison and Scott, who first invented this. They called it mu-tau reflection symmetry. They did it slightly differently. They said that these two rows were complex conjugates of each other, but it has the same effect. It leads to the same physics. but Harrison and Scott were the first people to discuss that. Okay, and also Harrison and Scott, together with Perkins, around about the same time, proposed something called tri-bimaximal mixing, which was basically to assume that all of these three elements were identically equal. Okay, not just approximately, but identical. So it was perfect tri-maximal mixing. That constrains, as I think Denjo already spotted, that constrains this angle θ13, or rather the sine of the angle θ13, to be 1/√3. So that assumption fixes that angle. The bimaximal part of it fixes sine θ23 to be 1/√2, so that when you square it, you get a half. And obviously, when you square this, you get a third. And the original proposal had θ13, which are fine. These agree with current data at 3 sigma. But this one here is excluded now at many sigma. So they proposed that you would have a 0 there. And that's excluded because we now know that that's θ13 is definitely not 0. Okay, in fact, the best fit preference these days is sine squared θ12 is less than a third. So this tri-maximal prediction is still allowed at 3 sigma, but if you want the actual absolute best fit, you need a little deviation from it, but it's still pretty good. But this is the main problem, reactor angle. Okay, so one can extend this idea. In fact, you can keep these good predictions, keep the tri-maximal mixing and bimaximal mixing, and now introduce a θ13. So if you apply the constraint that you have a 2-to-1 ratio between these elements here, so that's what's written here, UE2 squared over UE1 squared is a half, and well, this is 1-to-1 as usual, then that implies mathematically a matrix that looks like this. So you can switch on the reactor angle now by still preserving tri-bimaximal mixing. So this is called tri-bimaximal reactor mixing, and it's a way of switching on the reactor angle while preserving tri-bimaximal solar and atmospheric mixing. Another approach to data is to say, well, okay, maybe we can keep the original Harrison-Perkins-Scott tri-bimaximal matrix, and maybe that just applies to the neutrinos, and that we need to add some charge lepton corrections to it. Remember that the physical PMNS matrix is the product of a charged lepton rotation and a neutrino rotation. I skimmed over it, but it was on one of the slides where I was comparing the CKM derivation from the Lagrangian to the PMNS derivation from the Lagrangian, and you can see that it is possible to keep the tri-bimaximal mixing, but just purely theoretically in the neutrino sector, and introduce some charged lepton rotations. Now, if you just multiply these two matrices together, you end up with a matrix that has this form here, and you can see that this 0 gets filled in. It's quite amusing, even though neither of these matrices have a non-zero element in the 1-3. When you multiply them together, a 1-3 element is generated. So this is an interesting way of generating the 1-3 element, and it's proportional to the charged lepton angle. Okay, sine θ1 to E. And this little formula here, this 1/√2, comes about because of what happens when you multiply these matrices together. I mean, basically this 1/√2 is playing a role here. And this suggests that the charged lepton angle should be of order the Cabibbo angle, which is quite interesting. Okay. On the other hand, when you multiply these two matrices together, this bottom row here doesn't get changed at all. So because you're doing just, if you just multiply them together, you can see this bottom row. I mean, those of you that are good at doing matrices in your head will be able to see immediately that this bottom row is unchanged by this matrix multiplication. And the fact that it's unchanged leads to some predictions. It predicts that the ratio of this element to this element, so this is u tau 1 and this is u tau 2. If you take the ratio of these two elements then and compare that to the particle data group parameterization of PM&S matrix, you get this complicated relation here. But you can actually solve this for cos delta. It's not difficult to rearrange this and get an expression for cos delta equals something, and that's what this is here. That gives cos delta equals something, and this actually gives you a prediction for the CP phase in terms of these angles, in terms of the angles. So you can make a prediction for that, for the CP phase, assuming this structure here. Okay, it also predicts that sine squared theta 2,3 is less than a half. So this would be the first octant being predicted.
Steve, can I ask on that last slide there before you go, when you have theta 1, 2 being approximately the same as theta c, if you put theta c into the charged electron rotation, what would happen if you just used the CKM matrix there? Would that be compatible with the experiment?
I mean, if you used exactly
for the charged electron rotation, if you just stuck the CKM matrix in there. Yeah.
Oh yeah, I see what you mean.
In other words, could U PM&S times the inverse of U CKM be something elegant?
Yeah. So you would get something with a richer structure than this. You would lose this prediction because you would be already putting in something non-zero for theta 1,3 there. So you'd be putting in VUB, right? It's the VUB element of the CKM, or well, yeah. So you'd be putting in that. So this wouldn't be. So here you would have two terms. You'd have one coming from the matrix product, and then you'd have another term coming from the actual primordial value of VUB itself. So yes. It would be a little more complicated than this. Yeah, but that's interesting idea. Yeah. Mm-hmm. Interesting. I should say that this doesn't work exactly. This little relation here would predict an angle of I think 9 degrees, which is a little bit on the large side. But this is actually outside of the observation. So it doesn't quite work perfectly, but it's suggestive of an angle of order theta equivalent. But you could do that. You could pretend that this charged lepton rotation were exactly equal to the CKM. And I'm just trying to think if people have written papers on that. I think Smirnov has certainly pushed something like that. So yeah, I'd have to look up Smirnov's papers, but yeah, he's done something like that where he would put in the I think he puts in the whole matrix, but I'd have to look it up. Yeah, I can't remember off the top of my head. But it's an interesting idea.
So I'm a little unclear as to the tri-bimaximal matrix. There doesn't seem to be really an enhanced symmetry associated because of the eigenvalues are different. So
excellent, Denjo. That's really great question, because I'm going to come on to that later. The symmetries that can explain the tri-bimaximal matrix. Yeah, that's exactly what I'm going to get onto. I mean, clearly that looks like it's some kind of weird symmetry, because you've got these kind of permutation symmetries going on here somehow, or three-fold symmetry here and two-fold symmetry here. So you've got kind of a Z3 and a Z2 going on, but not quite, because but it's actually interesting. I will definitely discuss that point later on. Yeah, so far what I'm doing now, I should give you a plan of what I'm doing. I'm just doing a phenomenological ad hoc survey of what could work experimentally, and then the next pass through I'm going to be imposing theoretical symmetries which enforce these ad hoc patterns. So that's my strategy. So first of all, I'm doing something very phenomenological and ad hoc, and then later on I'm going to be looking at symmetries. This could be a long seminar. So I hope we get through it. That would be great. Right, so another possibility. So all these possibilities are because this 1,3 element was measured to be non-zero. If it was zero, if theta 1,3 were measured to be zero, I wouldn't have to do any of this. So I wouldn't have to do any complicated stuff. So I'm doing this complicated stuff because theta 1,3 were measured to be non-zero. So another thing you can do is to say, well, let's retreat a little bit from tri-bimaximal mixing and just have tri-maximal mixing. So suppose that only this column, the elements were equal in this column, and we're just agnostic about what goes on in the rest of the matrix. So in other words, you just impose the second column being 1/√3s, and then you just say that the other columns could be whatever they want to be, only constrained by unitarity. So that's called tri-maximal 2, because you've imposed the third column of the tri-bimaximal matrix. There's also something called tri-maximal 1, which is where you impose the first column of the tri-bimaximal matrix. I just remind you what the tri-bimaximal matrix is. That's the tri-bimaximal matrix there. So the first column also has a structure, and you can also ask yourself, what would happen if I impose that first column and let the rest of the elements do what they want? And that's called tri-maximal 1. So that's this one here, TM1. It's where you just impose the first column to be that, and then the other elements can be whatever they want. And you can, and these ansatses come with predictions, as we'll see now. So TM2 comes with the prediction of these angles here. So UE2 predicts this combination to be 1/√3. So this actually predicts sine squared theta 1,2 to be slightly greater than the third, which is a little bit disfavored actually. But the other, this element here would predict this, this would predict this. If you take the ratio again, you can get a prediction eventually for the CP phase. So this would be the prediction of the CP phase. It's a different formula to what we had before, but it's still a prediction for the CP phase. So that's the game. You predict the parameter that hasn't yet been measured. Okay, that's TM1, or TM2. So TM1 is, you play a similar game. In this case, you would predict that sine squared theta 1,2 was less than the third, which is actually good. This is favored. This is what the data tells us. Slightly less than the third. It's consistent with being equal to a third at 3 sigma, but at 1 sigma, there's a preference for being less than the third. And then similarly, these two elements would eventually give you a prediction for the CP phase, a different formula from this. So again, you can test this against data. Eventually, when these future oscillation experiments are built, you can then ask, does it agree with your prediction?
But both of them say that cos delta is 1, right?
Sorry, Venus, say again?
Both of these situations lead to cos of delta being 1, right? Because if I remember correctly, cos of delta was u mu2 divided by u tau 2.
So cos, you said cos delta.
Oh, sorry. Yeah. yeah, I see at the bottom it's a different,
Yeah.
different setup.
Yeah.
I see.
Yeah.
Mhm.
Mhm.
Can I ask a question? The
Sure.
right-hand side of cos delta is not bounded. As is. For example, if the cotangent of delta can become infinite.
True.
So what
But
does it formula mean?
well, these, yeah, I haven't actually. That's a very good point. I haven't actually said this yet, but in the definition of the PD particle data group parameterization of the PM&S matrix, these angles are in fact bounded. They're not allowed to be small. They're within well-defined ranges. So they. But I think the allowed value would still allow this to be infinite. But the point is that experimentally, we know that θ23 is close to 45 degrees. So this thing here is actually quite close. θ23 is quite close to 45 degrees. So tan. So these are actually quite well known parameters.
And what
So
about
you can
S13? S13
Sorry?
can become 0. Suppose S13 becomes 0 or 1/3, 1 over root 3.
Well, again, we know what this is. This. Oh, you mean if sine squared were a third? Yeah. Well, this is something bad would go wrong. But these formulas, we know what these are. We know that θ13 is about sine θ13 is about 0.15. So these are known numbers. So although mathematically these predictions could be pathological, physically they have well, you know, they have well-defined meanings within the range of the experimentally allowed parameters. So you never hit these singularities.
And if we know that θ23 is very close to 45 degrees,
Yep.
that means cotangent of 2 θ23 is close to 0. So
yes, I guess that's right. Yeah.
So that means both of them are predicting that the CP violating angle is.
Well, cos
around
delta would be, cos delta was predicted to be small. That's right. That's right.
Yeah.
In this prediction. So I think to really, I should really have included or could include some plots of these predictions, and then you could see actually what the cos delta was predicted. But there's lots of papers on this. Well, if you look in these references here, Albright and Roeder-Johan and collaborators, you'll be able to see better. I think they have plots of these predictions. Okay. All right. So now I'm going to get on to symmetries, family symmetries. So how are we doing for time? So maybe we should take another break now while I get some more water. Keep my voice going. So is it okay to continue? Keep continuing?
Absolutely. I mean, yeah, I'll be available.
Yeah. What about everyone else? Is it okay if we continue, or, I mean, please just tell me how long you want me to continue.
I think Denju's on the phone.
Okay.
But yeah, I mean, I've attended a few of these seminars, and usually they go on for about 3 hours.
All right.
Yeah.
Okay. All right. So in that case,
yeah.
I definitely will get another glass of water then. In that case, yeah. All right.
Perfect.
This is a convenient place to pause anyway, because we're going to switch topics now to family symmetry. Yeah. So I'll be back in a couple of minutes. Yeah.
Perfect. Okay.
All right.
Sure.
Hello. Hello, can you hear me?
Yeah, yes, we can, yeah.
Okay, so is everyone still okay for me to continue?
Yes, I think so. Anyone that is not okay is leaving. You know,
Okay.
they will join back and watch the video. So it's not.
Okay, all right.
There are only possibilities they won't be able to ask questions, but that's a sacrifice. So
all right. Okay, so we'll see how we go.
Yeah.
Yeah. All right. Okay. Oh, I've got a question in the chat, which I haven't looked at. Sorry, I have to leave now. Really great talk so far. We'll set aside more time in future. Okay, that's okay. So someone's
Sinead has to leave, and she was just apologizing, saying she'll watch the video, so she's going to.
Okay, fantastic. So yeah, please feel free just to tell me if you've had enough, or if people really.
Well, we are very relaxed. We understand that some people have to leave, and that's fine. You know.
Okay.
So the applause is going to be light at the end, but it will be light anyway.
Okay. All right.
Hopefully the speaker doesn't have to leave early.
I just keep going. Let me set a cutoff of it's 4 o'clock now. Shall we set a cutoff of 5? 5 o'clock?
Well, yes, 6 is probably a better cutoff, but just to be on the safe side. That's
this is amazing. Yeah. Well, the cutoff will be when I get to the conclusion.
Okay. All right.
Let's see how far we go. Right. So family symmetries. Let's change topics now to family symmetries. So here's a few family symmetries that have been used to explain these patterns that I've been talking about: tribimaximal mixing and trimaximal mixing 1 and all that. These are some of the groups that have been used. They're all subgroups of SU3. So SU3 continuous group, everybody knows about, and these are some discrete subgroups of SU3, which I guess some people will know about. Some lattice theorists will know about some of these subgroups. This is S4 symmetry, delta 96. They're all given these funny names, but okay. These, well, A5 is the symmetry of a icosahedron in the shape of a soccer ball here. A4 is the symmetry of a tetrahedron, rigid symmetry of a tetrahedron. S4 symmetry of a cube, and so on. Okay, so these Platonic solids, like we said, these Platonic solids actually are related to these different groups. So A4 is the symmetry of the tetrahedron, and actually these were known. These go back to Plato's time. So Plato associated these solids with fire, air, earth, and water. And in terms of neutrino physics, the history of the use of these discrete groups goes back to Ernest Marr and Rajasekharan in 2001, who were the first people to propose that A4 can enforce tribomaximal mixing. So that corresponds to your question, Denjo, about what symmetry can enforce tribomaximal mixing.
I think the Archimedeans wouldn't have been very happy with you using the dodecahedron there, but that's another story.
Is that not a Platonic solid?
It is, but it's one of those they like to keep hidden, wasn't it?
Oh, I don't know. Okay. I've actually I bought a set of Platonic solids off the internet, so I've got a little set of them on my desk here. But yeah, I don't know the history of the which ones were publicized and so on. Okay, but for the purpose of this talk, I think it's enough to just focus on some of the simpler ones. So let's focus on A4 and S4. So A4 you can write in terms of two generators, S and T, which are written here. And S4 is kind of extension of A4 in some way to include another generator called U. These boldface symbols here are the representation theory, the irreducible representations of the different groups. So A4 has one triplet, a singlet, and two non-trivial one-dimensional representations. S4 is similar, but it has two triplets, a doublet, and two inequivalent, well, one non-trivial singlet, one trivial singlet. These are some, I mean, the matrix representation of these generators is basis dependent, but in some basis, you can write the generators like this. And the connection with the tri-bimaximal mixing is that these two generators, this S generator in this basis, and also this U generator, can be diagonalized by the tri-bimaximal matrix. So that's the connection. So that's how you make the connection with A4. These two generators in this basis can be diagonalized by the tri-bimaximal mixing matrix. So here's how to get tri-bimaximal mixing from S4. So we start with an S4 symmetry, which has these three generators, S, T, and U. And the idea is that one of these generators, the T generator, is preserved. Well, S4 is broken. Let me say that first. S4 is broken, so we don't see exact family symmetries in nature. So the S4 has to be broken. If it weren't broken, then that would mean the electron, muon, and tau masses, charged lepton masses, would be equal. So we definitely have to break the symmetry. And but to explain tri-bimaximal mixing, you have to break it in a rather special way. You have to break it such that the T generator is preserved in the charged lepton sector, and the S and U generators are preserved in the neutrino sector, because we already observed that the S and U generators are the ones related to tri-bimaximal mixing. So these are the ones, these two generators are the ones that we want to preserve in the neutrino sector.
Sorry, Steve, by tri-bimaximal mixing, you mean the one just for the neutrinos, right? Because otherwise, I thought the tri-bimaximal, which says θ13 is equal to 0, is ruled out.
That's right. So I'm coming to that exactly.
Okay.
I'm exactly coming to that, Venus. Precisely. Thank you. I'm coming to that, but so far I'm just pretending that tri-bimaximal mixing is okay at the moment. And then on the next slide, I'm going to say, well, it's not okay. How do we change this picture? Yeah, but just bear with it just for one slide. Suppose that tri-bimaximal mixing was okay. This is how you could explain it. So this with this symmetry preserved in these symmetries preserved in these different sectors, we would end up. You can prove that it would lead to the tri-bimaximal mixing matrix, which, as you correctly said, is excluded. So something has to change. And what you need to do is you need to break one or more of these generators, S, T, and U, because if you preserve T, this T generator leads to a diagonal charged lepton matrix. So in fact, in this basis, you can see the T generator is diagonal. So that actually enforces a diagonal charged lepton mass matrix. And this would preserve a tri-bimaximal neutrino matrix. So you would end up with a total PMNS matrix being tri-bimaximal. But that's excluded. So we need to do something.
So first of all, a nearly diagonal charged lepton mass matrix is not ruled out. I mean, it is. We haven't seen any mu tau mixing.
So yeah, all I'm saying is I think that this in this basis at least, if we work in this, because it's all very basis dependent. If we work in this particular basis,
Yeah.
we're doing S4 and we're working in this particular basis. In this particular basis, the charge lepton mass matrix was diagonal. The elements are not equal. The ME, the MU, the M tau, they're not equal, but they're diagonal.
Yeah, yeah, but that's not far away from reality.
Well, this unfortunately this.
Oh, this bit is, yeah.
This bit is, yeah, exactly. So this is, yeah. So that bit's okay. The bit that's not okay is this 0 here. Yeah, exactly. So we need to do something.
Yeah.
Yeah.
So just before this, we were talking about, you know, having a tribimaximal in the neutrino bit, but having it multiplied by the charge lepton, let's say, some kind of mixing matrix. Yeah.
By the mixing matrix that diagonalizes the charge lepton matrix. But because in this basis, the charge lepton mass matrix is already diagonal,
I see.
then that matrix just becomes a trivial unit matrix.
Yeah. Right. So it doesn't work. Perfect. Thank you.
Okay, so one thing you can do is to break the T generator. If you break the T generator, then this would mean that the charge lepton matrix is no longer diagonal, which is, I think, what you were kind of driving at before. In that case,
can I ask a question? I have something. This STU, why are there are just 3 generators of S4? Why are they picked? For example, there is a system of 2 generators, namely the fully cyclic subgroup and any transposition.
That's right.
So why don't we consider that? Is simpler than?
Yeah, it's simpler. It's simpler in terms of the number. I agree with you. I agree with you. You can do your group theory of S4 with 2 generators. In fact, the choice of generators is the algebra of the generators is a choice, a certain possible value. So I'm choosing the basis of the generators where I have 3. I find that it's just by trial and error, really. By trial and error, that basis turns out to be the most convenient basis of the generators for the purpose of applying the group theory to tribimaximal mixing.
But I don't see the physics behind this choice.
Well, the physics behind the choice is given here. The physics behind the choice is that in this basis, the S matrix and the U matrix are diagonalized by the tribimaximal matrix, and the T matrix is already diagonal. So that means that in this basis, this T generator will enforce a diagonal charge lepton mass matrix, and these 2 matrices will enforce a tribimaximal neutrino mixing matrix. So I'm sort of giving you the answer. I'm not giving you the trial and error bit, which led people to choose this basis, but I'm giving you the answer. The answer is that this turns out to be the most convenient basis of generators. It's not the most minimal choice. Indeed, you can have a what's it called? Keep trying to think of the name. Presentation. That's it. You can have a different presentation of the generators where you only have 2 generators. In fact, all of that is discussed in this review here. We discussed the different presentations, but this is a convenient presentation from the standpoint of applying group theory to tribimaximal mixing. Although I agree, it's not obvious. But once I've given you the answer, it is obvious because you can see that it works. But getting the answer was not obvious. So that's why Ma and Rajasekhar and well, actually they studied A4, not S4. But subsequent authors showed that it's actually S4 is the one that really enforces tribimaximal mixing, not A4. Okay.
Okay.
Okay, great. So so then if we already said that if T is preserved, that means charged lepton mass matrix diagonal. That means that the mixing matrix from the charged lepton sector is the unit matrix. But once the T is broken, that leads back to these charged lepton rotations. So then, so we would, if you break the T generator, then you would get back to this idea of a charged lepton rotation acting on the PMNS, on the tribomaximal neutrino matrix. Okay, so that's one possibility. Another possibility is that you break the U generator. If you break the U generator, just keep the S generator, it turns out that that would enforce TM2, which previously we just wrote down ad hoc, but this structure, TM2 structure with the second column preserved, is enforced by the T generator in the charged lepton sector and the S generator in the neutrino sector.
And who's breaking the generators?
It's so what's breaking the generators is different choices of these Higgses. You see, the S4 is broken by Higgses, and different Higgses in the charged lepton sector and the neutrino sector. These Higgses are what people call flavons, but they're basically Higgses. They're Higgses that break the S4. So if you, it's all about not just the choice of Higgses, but the choice of vacuum alignment of those Higgses as well, which is a bit of a black art, really, because vacuum alignment, it's pretty messy business to get the vacuum alignment to work out. But I'm definitely not going to get into that.
And presumably these Higgsons are meant to be very massive.
Yeah, these Higgses are very much, but yeah, it's a good point. It depends on the scale at which this symmetry is broken, but certainly it could be as low as a TV scale. So people talk about these flavons being around at the TV scale. Yeah, so it could be TV scale, or it could be much heavier. So if you're interested in grand unified theories, sorry.
The flavons have no gauge symmetries; they're just flavor, are they?
Yes, that's right.
The Higgses
yeah,
are not. They don't have any gauge. They're just flavor.
Precisely, yeah. So the definition of a flavon is something that only carries the S4. It doesn't carry any standard model quantum numbers. Okay. All right. So that's another possibility. A third possibility is that actually you break S and U, but you preserve the combination SU. And the reason this is interesting is because it leads to TM1, where you preserve the first column. So this was shown by these authors that the combination of SU and T will enforce that first column having that TM1 structure. So all these structures that we just pulled out of a hat earlier on, they're actually, all of them one by one can be enforced by different symmetries. So that's a motivation for some underlying family symmetry. Okay, so the next question is, what is the origin of these symmetries, Plato's symmetries? And there's two possibilities, at least two possibilities. One possibility is that these discrete symmetries come from some gauge group, SU3 or SO3, which is broken down, maybe by some Higgses in large representations, to SU3, to A4 or whatever. I think I've got a backup slide on that, but I don't plan on talking about it because it's not so fashionable. What's more fashionable is, in fact, in the past couple of years, it's become very fashionable, is to look at superstring theory and modular symmetry as the origin of these groups. And I thought this would be more interest to the DS group to say a few words about modulus. I'm by no means an expert on this, but I've worked on it a little bit. And I'm going to say a few words about the modular symmetry. Are you familiar at all with the idea of modular symmetry in string theory?
Yes,
not.
to some extent, yeah.
Okay.
Some people will be, some people won't.
Sorry?
Some people will be familiar, but some people won't. So
Okay, all right.
you know,
So I've just got a couple of slides on this anyway.
Before you go to the modular symmetries, could I just ask, how many of these flavons do we require? I mean, is it just the one flavon that gives mass, I guess, then to charged leptons and neutrinos? Or
so you need at least two. You need one associated with the charged lepton sector. Yeah, let me go back right in the beginning. There was this little thing here. These are the flavons, these phi L and phi nu. These are flavons which are new Higgs fields which break the flavor symmetry. So you need two of them at least. One in the charged lepton sector and one in the neutrino sector.
Yeah, perfect. Thank you.
Okay, so here we go. So for those, I'm afraid this is going to be a little bit telegraphic. So for those of you that know this is easy stuff. But for those of you that don't know it, it's going to be hard to learn it from this. It's pretty formal stuff. It goes back to the idea of n=1 global supersymmetry, which has a modular invariant action. So it goes back to Ferrara in 1989. So the key thing is supersymmetry. You need supersymmetry for this to work. So you have your action, which looks like this. This is the usual superpotential. This is the Kähler potential, and the Kähler potential, unfortunately, is not fixed at all by modular symmetry, as was very quickly pointed out. As soon as Ferruglio proposed this, very quickly these people jumped up and said, oh, it doesn't fix the Kähler potential, so therefore there's all these uncertainties and so on. So I'm going to ignore, in what I'm going to mention, I'm going to ignore the Kähler potential uncertainty and just assume ad hoc that it's a minimal Kähler potential. This tau is this modulus field. I'm going to assume one modulus field. The modulus field is, in string theory, is the field that fixes the shape of the extra dimensional compactification. There are usually many moduli fields. So most papers which have been written assume only one modulus field, but I guess you have to start somewhere. So I'm going to assume one modulus field to start with. And if you do that, then your superpotential, this is supersymmetric, the superpotential involves superfields, phi1, phi2, so on. And this is the Yukawa coupling. So these Y's are the Yukawa couplings. And in string theory, these Yukawa couplings are determined by the modulus field tau. So these Yukawa couplings are fixed. In fact, they're modular forms. If these modular weights of these fields are 0, then this could be trivial Yukawa coupling. But if these modular weights add up to something that's not 0, then necessarily, if you enforce modular symmetry, these Yukawa couplings have to be so-called modular forms. This is how the modulus, this is the usual symmetry that the moduli fields obey. This is familiar to all string theorists. And this is how the superfields transform. See, it depends on the modular weight. So this particular one has a modular weight Ki. Okay, this row is saying that these fields form some representation of a group. I'll come on to that shortly. So they transform as some representation of a group, and then they transform by this other factor, which depends on the modular weight.
But SL2Z is infinite dimensional.
Yes, you're quite right. Yeah.
So why fix a
because
finite dimensional group?
I'm going to be modding out by a certain group in order to make it finite dimensional. But that comes on the next slide. So just hold on until the next slide. These are the, this is how the Yukawa coupling, the modular form, transforms under the modular symmetry. Okay, and modular invariance requires that the modular weight of the Yukawa coupling balances the modular weight. So the modular weight of the Yukawa coupling in blue balances the modular weight of the sum of the fields there. So that's what this equation is, balancing of modular weights. This equation is saying these rows are representations of the finite modular group, and it's saying that the product of the representation of the Yukawa coupling and the representations of the superfields must contain a singlet. So it must be invariant under the finite modular group. Okay, so as you mentioned.
Sorry, Steve, can I just ask, what do you mean by the finite modular group? And I mean, the modular group is infinite order.
That's right. So that's explained. It's supposed to. Yeah, that's what I'm coming to now, I think. But very brief, yeah. very briefly. So this is almost certainly not going to satisfy you, but let me show you what I have, and then you can. It's a starting point anyway. First of all, I want to say a little bit more about modular forms. What are modular forms? For those people that have never seen them, they're holomorphic functions, and they transform like this. So this is the Yukawa coupling, transforms in a certain way under this gamma bar group. Okay, this is the infinite group here. Okay, and it depends on, it's parameterized by a certain level, n, which is a positive integer. So n could be 2, 3, 4, 5, and so on. And k is the modular weight here associated with the modular form. So the modular form is governed by two integers. It's the modular weight and the level. Now the group is given by the group of all these transformations A, B, C, D, which we had on the previous slide. And this is, it's basically equal to this gamma bar group, which is the unit matrix mod n. Okay, so I'm not going to get into this, but that defines the infinite modular group. And what else? Modular weight k and the level n form a linear space, and they can be decomposed into irreducible representations of a finite modular group. So this was Furuglio's work in 2017. And under the finite modular group, the modular forms transform like as follows. It's the same as above, except that this row here is a unitary representation of a finite modular group, gamma n, without the bar. And that's given by gamma bar, the infinite group, modded out by this gamma of n. And the finite modular group is determined by two generators, S and T. S and T are not quite the same as the S and T we had before. The meaning of S and T now is that these are the generators that give you the modular symmetry. So they tau goes into -1 over tau. There's the S generator, and the T generator is tau goes into tau +1. So these are the basically these are the transformations on the lattice of when you're doing your compactification. You compactify on a discrete orbifold, which can be represented by a lattice, and these are basically the lattice vectors, the transformation of the lattice vectors under which the lattice remains unchanged. That's the meaning of the modular symmetry. And the finite modular symmetry has this not only s squared is equal to 1 and st cubed is equal to 1, which is the normal modular symmetry algebra for the generators, which you can convince yourself from these transformations. But also there's an additional one which makes it finite, and that is the imposition of this t to the power of n is equal to 1, and that brings in this level n here. If you impose on the additional requirement that t to the power of n is equal to 1, then that actually defines this finite modular group gamma n.
Well, presumably it's a toroidal compactification where you have rational angles for the torus.
Yes,
Yeah.
exactly.
Okay.
So it's a toroidal, exactly. It's a toroidal compactification. It's basically, I'm thinking of Orbifold type compactifications with the toroidal compactifications. Exactly. So this is, I think this is what we have in mind here. Yeah, exactly. All right. So here's some examples then of different levels, 2, 3, 4, up to 7. This is the dimension of the representation in terms of k. Depends. Remember, the modular form depends on 2 integers, k and n. So once you've fixed n, you still have a choice of k. So k is the modular weight of the Yukawa coupling. And depending on the modular weight of the Yukawa coupling, then this gives you the dimension of the particular representation, which is reducible. You have to then reduce that. That decomposes into irreducible representations, which is what this row is. These are actually irreducible representations. This is the dimension of the group, of the finite modular group, and this is the user-friendly identification of what these modular groups are. So n equals 2 corresponds to S3, n equals 3 corresponds to A4, n equals 4 corresponds to S4, n equals 5, A5, and so on. So the group that was studied by Ferruglio, who really started this field off in 2017, although it was well known to string theorists, but he brought string theory applications into the neutrino. He applied it to neutrino sector. He mainly focused on this A4 example here, this level 3, but people have studied all different sorts of levels since then. So for the purpose of this talk, I'm going to study Ferruglio's original example, which is what I'm doing on the next slide. Do you see that? Is this obscuring your screen, this bar? I don't know how to remove it.
No, it seems to be fine.
Oh, okay, it's just me then. Yeah.
I don't see anything that we see the full screen.
Okay, great, fantastic. Okay, so this is a brief example of the use of these modular forms. So this is A4, the one that was studied by Ferruglio. So we already said that Yukawa couplings involving twisted states whose modular weights do not add up to 0 have to be modular forms in order to satisfy modular symmetry. So for example, if we choose a level 3, that's n equals 3, a weight 2, that's k equals 2, then the Yukawa couplings decompose into various representations, one of which is a triplet. So this gives you a triplet of A4, and the triplet depends on these numbers here. So this is, I think these are the Dedekind expansions, and these Qs represent e to the 2 pi I times tau, and tau is the modulus field, the complex modulus field, which in terms of some compactification will be the ratio of 2 lattice vectors in it. Okay, if you're familiar with this, then that's fine. If you're not, don't worry about it. You can think of just tau as just a complex free modulus field. It's a complex number, which is a free parameter. So these Qs depend on one complex free parameter. And if we consider this operator here, this is the operator, the classic Weinberg operator, which can be responsible for neutrino mass. Then you've got 2 Higgs fields here, 2 lepton fields. if the lepton fields are triplets here, then the Yukawa and the modular weights don't add up to 0, then Yukawa coupling has to be a modular form, and that has to also be a triplet, because the only way to get a singlet, if these L's are triplets, then the only way to get an overall singlet is if the Yukawa coupling itself is a triplet, transforms as a triplet. So in other words, like this here. And if you multiply this out to look at the singlet and extract the neutrino mass matrix, you will get a mass matrix like this, where Y1, Y2, Y3 are the components here. Y1, Y2, Y3 are these 3 components here, and they depend on Q. So what you've done is you've expressed the entire neutrino mass matrix in terms of one free parameter, tau, because these Y1, Y2, Y3s are fixed in terms of Qs, and the Qs only depend on one complex parameter. So you've got some predictive power in this. The problem is that you've got too much predictive power, because this, as Ferruglio showed in his paper, this actually gives you the wrong prediction for this doesn't agree with data, but it's nevertheless the simplest example of the use of modular forms to get neutrino mass matrices. So
Ferruglio used it for A4, I'm guessing, right?
Yeah. So his paper, I mean, I think he listed the other groups, but he applied it to A4, which was the simplest group that contains triplets.
And have other people tried it for larger groups with triplet representations?
That's what all these papers are. There's been quite a lot of activity on this. So people have, one by one, they've gone through all these groups here, and even up to sigma 168, which is the level 7 group. People have stopped there for the moment. But.
And any of them give a acceptable?
Yes.
But presumably S4 is the one you want to look at, is it?
Yeah, S4. Yeah, S4, exactly, Denjo, exactly. Yeah, so S4 can give something interesting. Yeah, so most of these papers give some results which agree with phenomenology.
Mm-hmm.
Yeah, that's right. So I invite you to just have a look at. Certainly, I'm not going to say any more about this now. I'm going to now switch topics to the measurement of neutrino mass. I wonder if I can figure out how to stop this bar appearing. I've got this little toolbar here, which is.
Oh yeah, those are annoying, but they're only visible to you, so we can't.
Okay.
We can't tell you
All
what
right.
to do with them. You can move if you can move it to some. I think you can move it to some place out of your way on the screen with your mouse.
Yeah, I've moved it exactly. I've moved it to the bottom.
But we can't see it, so it's
okay. Fantastic, fantastic. All right. So now we're going to switch topics again and discuss measuring neutrino mass, which I think was somebody asked about this earlier on, about how to measure neutrino mass from CMB.
Yes, bar last.
Exactly. So so the current limit, I'm just going to, this is rather an old limit, but the limit hasn't changed very much actually. So this limit is still pretty robust. There are more speculative, more modern limits, but the basic limit is that, which people still quote, is that the sum of neutrino masses, so this is m nu1 plus m nu2 plus m nu3, is less than 0.23 electron volts. And that you get from this fitting the CMB. This was also mentioned as well. I think Denjo, you mentioned this about the number of effective neutrino species. So the fit is about 3, but 4 is a little bit disfavored here. So so this is the data in the neutrino number of effective species against neutrino mass sum plane. Okay, that's cosmology. In the laboratory, you can also get limits. There's either, well, neutrinoless double beta decay gives you the strongest limits on neutrino mass. This is ordinary beta decay on the left, where you have 2 beta decays of a nucleus, giving 2 neutrinos in the final state. This is neutrinoless double beta decay, where these neutrinos annihilate and you only have 2 electrons in the final state. And this is only possible if neutrinos are Majorana. This annihilation of neutrinos would prove that the neutrinos are Majorana particles, which is the correct way to say it. And also you get a limit on the neutrino mass of about 0.2 electron volts for this actually gives you, only limits the first entry of the neutrino mass matrix, because it's connecting nu E to nu E.
So that's how you get a mass limit.
So that's exactly, that's right. That limits the first entry of the neutrino mass matrix. Okay, and the other, so this is neutrinoless double beta decay on the right, which we've been talking about just now. You've also got single beta decay, tritium beta decay, and that leads to limits, direct limits of neutrino mass. So here the neutrino doesn't have to be Majorana, it could be Majorana or Dirac, and the quantity that you're actually sensitive to is defined by this equation here, where this is the PMNS matrix elements here. The present Mainz limit is 2.2 electron volts, but just this year, I think it was this year, Catherine, the brand new experiment, has released its first limit, and its first limit is 1.1 electron volts. So that's already exceeded the Mainz limit. And in the future, Catherine can go down to 0.35 or so electron volts. So that's that. And on the right, you've got the limits of neutrinoless double beta decay. Now, let me move that up to the top. So here I'm plotting, this is the neutrino mass scale, M0. So this is the lightest. This is what I called M1 before, actually. This is plotting N1 against the neutrinoless double beta decay parameter, which is defined here. This actually, although it doesn't look like it, this is actually equivalent to the first entry of the neutrino mass matrix. You can prove that. The current experiments bring you down to this blue line here, or maybe a little bit further now. This is quite a few years old. The next generation of experiments, their goal is to take this blue line below the inverted hierarchy limit here. So this blue line is going to fall. It's going to cover the whole of the inverted hierarchy region here, looking for neutrinoless double beta decay. If this will be spectacular news if they ever find it, because it will be proving it will not only give you the absolute scale of neutrino mass, but it will also prove that neutrinos are Majorana particles. So it will be one of those spectacular experimental results.
And when can we expect that result?
Well, all these experiments are running in various times, and every year you get updates, and this blue bar is sinking. I think it's already touching the top of this band, actually. But certainly over the next several years, they should cover the inverted region. It's not a long time scale.
Excellent. Yeah, that's excellent. And is there any reason to believe that the mass is actually there's a lower limit, a lower bound?
No, not really.
Unfortunately,
Unfortunately not, because, well, if neutrinos have this inverted ordering, which I still think cyclic ordering is a better name for it, but if they have this inverted ordering, then you'll definitely be able to discover or exclude that.
Yes, exactly. Okay.
Yeah, but if neutrinos have this normal ordering, then unfortunately this thing can dive all the way to zero.
Which you suggested, you told us that normal ordering is more probable based on current evidence. So
correct,
yeah,
correct.
okay.
It's preferred by current data. So right.
And on the left, the limit that we get from Katrin is also on the mass of the first neutrino, right? That's not the limit on the sum of the neutrino masses.
That's right. So this is the definition of this 1.1 electron volt is the square root of this this mass here.
Yeah.
So it's sort of a measure of the neutrino mass. It's a measure of, so you're measuring the electron neutrino mass in quotes, but really, if you ask me what I mean by that, then I have to just resort to this equation. What I mean by that is the weighted sum here. Yeah. This is the thing that the experiment's sensitive to. It's the weighted sum of neutrino masses squared, and then you square root it to get the limit.
Yeah.
So yeah, that's the precise meaning of what this limits. Exactly, and this is the precise meaning of what this m beta beta is.
Yeah, which is the same thing, it seems, just square
it's
root of that.
Yeah, so there's a subtle difference, which is, first of all, it's linear equation. Secondly, this is the modulus of the elements squared, whereas this is not the modulus of the element squared. It's just the element squared. So it's not that I've missed out the modulus sign. There isn't a modulus sign. The fact that there isn't a modulus sign means that the Majorana phases actually can be playing a role in here.
Good point. Yeah.
So whereas here they cannot, because I'm taking the modulus. Here the Majorana phases can be playing a role.
Ooh, so
it's not obvious why that's real. Is it easy to see why that's expression?
No, you're right. Yeah, so yeah, well spotted. I should be taking the modulus of this whole thing.
Okay.
Yeah. So this m beta beta is the modulus. Okay. There's missing modulus signs here. Sorry about that. Yeah, there should be big modulus signs here. This is the modulus of this weighted sum on the right hand side. Thank you. Yeah, that's a typo or an omission. Yeah, should be modulus signs. Sorry about that.
So the Majorana phase could be playing a role here, but we won't be able to tell what it is.
It's going to be tough to tell what it is. But first of all, we have to measure a signal. At the moment, there's no signal for this. Once you've measured a signal, then you've got to disentangle what those phases are, and that will depend on accurate knowledge of what these mixing angles are and masses. So it's going to be quite difficult to determine the phases. Although, as a matter of principle,
but in principle you could do it. In principle, you could do it if you can get the sum of the MIs from cosmological data and the delta m squared from neutrino oscillations. Then that would give you this formula would give you the Majorana angles.
I think that's right. Yeah, that's right.
Yeah.
So there is a way of finding out what these phases are. Yeah, absolutely. Yeah. All right, but first of all, you have to measure a signal, which we haven't yet. All right, so why is the neutrino mass so small? Just a quick look at the watch. Okay, 4:45. So I set myself a deadline of 5 o'clock, but we'll see. Why is the neutrino mass small? You can see from this figure, the neutrino masses are extremely small. The true masses have to be scaled. The true heights of these towers are scaled by these numbers. So the neutrino masses are really, really small. Majorana or Dirac. Okay, well, I'm not going to dwell on this. I think everyone knows, I think, what Dirac mass is, what a Majorana mass is. And you can have Majorana masses for right-handed neutrinos. You can write a roadmap of neutrino mass. So first question is whether neutrinos are Majorana or Dirac. If they're Dirac, that would tend to imply extra dimensional models. If they're Majorana, then you keep going down here. Do you see any extra Higgses at the LHC? If yes, then you can have Higgs triplet or loop models for neutrino mass. If no, you go down the list. Do you see R parity violating SUSY at the LHC? If yes, you can look at R parity violating SUSY models. If no, then you're down here. So right at the bottom, if you don't see anything at the LHC, you end up with the seesaw models. This is a cartoon of warped extra dimensions and how you can explain the smallness of neutrino mass by overlapping these wave functions. This is loop models of neutrino mass. This is a sort of zoo of models that people have proposed for explaining neutrino mass at 1, 2, or 3 loops. So, but you need, the key thing here is that you need these extra Higgses to do it. This has been recently a very famous model by Ernest Marr, scotogenic model. Historically, these were the famous models, the Z model and the Babu model.
So what's the meaning of the Scot in scotogenic?
Scotto is
question.
from the Greek meaning darkness, I believe.
Oh.
If I've got the etymology correct. Skotos meaning darkness, because this model can also explain dark matter as well, apparently. So this is also, is that right, Venus? Do you remember?
I think, yeah, I think the scotogenic model is kind of like the inert doubler model plus the seesaw that gives neutrino masses. So, yeah.
Okay.
But it doesn't have anything to do with the haggis, no?
I'm afraid not. No. No, it does look a bit like a haggis, doesn't it? But okay. R parity violating. This is a quick cartoon about R parity violation. Basically, you're using neutrino vevs with this stick diagram to generate neutrino mass, and the order of the neutrino mass is this neutrino vev over the neutralino mass, which is the particle appearing here. Okay, so these are the scales involved. Is Majorana mass renormalizable? Well, it could be. If neutrino mass is, I mean, basically I'm going through all the possibilities for the origin of neutrino mass. So one possibility is that you have a Higgs triplet. So delta is a light Higgs triplet with a very small vev. So if it's a Higgs triplet, then you can write a renormalizable Majorana mass like this. L stands for lepton doublet. On the other hand, if you only have Higgs doublets, then we have this Weinberg operator, which has the form LLHH. So 2 lepton doublets and 2 Higgs doublets. So when you put the vevs in for the Higgs doublet, and it has to be non-renormalizable because this has dimension 5, so 1 over mass. When you put the Higgs vevs in, then this would be Higgs vev squared over mass, and this gives a Majorana mass. And this is actually quite nice. People like this because it gives some reason for why neutrino masses are small. Because the mass goes like Higgs vev squared over m, so m could be some very large scale associated with this non-renormalizable operator. So that could give an indication of why neutrino masses are so light.
For the first option, so the bound that you have on the vev of, I guess, the delta is from rho parameter. It has nothing to do with neutrinos. So it's kind of,
right.
Yeah, some sort of a natural explanation, I guess. Can you call it that?
Yeah, I mean, certainly viable. But this delta is something you can look for in colliders, Higgs triplets. So it's testable. I don't. If you ask me, could this be excluded by LHC run 3 or run 2? I wouldn't. I don't know actually if you could exclude this. I guess not. But yeah, it'd be interesting. You could set limits on this from the LHC run. Certainly testable. Very, very testable. Okay, so people are very ambitious and they go beyond the non-renormalizable operator and they invent. Instead of having a non-renormalizable operator m, you can have a renormalizable theory where m is the mass of some heavy particle being exchanged. which could be a singlet or a triplet, SU2 singlet or SU2 triplet. So you can have diagrams in the S channel like this, or in the T channel like this. And these are not, these actually define the seesaw, the family of seesaw mechanisms.
Mhm.
It's exactly what seesaw mechanisms are. They're trying to replace the Weinberg operator by some renormalizable diagrams. Okay, so
Can I ask, sorry, before you go on, going back to your standard model picture, if you just took 3 right-handed sterile neutrinos, then they would generate that Weinberg operator at tree level through the
right.
Yukawa couplings.
Exactly.
And then the mass, that capital M would just, so they'd be singlets, and that capital M would be the mass of the Mariana mass. Is that a viable model? I mean, I keep hearing that sterile neutrinos are not viable.
Well, that's because there's this confusion about what people mean by sterile neutrinos, but we had that discussion before. So what is not viable is 1 electron volt sterile neutrinos, which mix strongly with ordinary neutrinos. That's not viable. What's definitely is viable is very heavy right-handed sterile or sterile neutrinos, like we discussed before. Yeah. But that's exactly right.
So it'd be quite possible. So it'd be quite possible to have the Weinberg operator coming from a renormalizable theory.
Exactly. Not only is it possible, Brian, but it's actually the #1 favorite mechanism for neutrino mass.
Ah, okay.
If you take a vote,
I'm pleased to hear that.
Yeah, if you take a vote of people,
but it doesn't give you a natural. It doesn't give you any natural explanation for why that mass is so heavy.
That's
You're
right.
just saying it's heavy for some other reason, which is not beyond that.
Some other reason. Then you have to. Then you know, like all good physics theories, it leads to more questions. So it leads to the question, why is it so heavy? And one possible answer, which I'm going to say now because we're not going to discuss it, I don't have any plan to discuss this, is that the right-handed neutrinos could emerge from a grand unified theory, such as SO10. In fact, the right-handed neutrinos have to be present. They're predicted by SO10, grand unified theory. And once you break the SO10, there's nothing to stop the right-handed neutrinos getting mass. So generically, SO10 models would predict this mass M being rather large, somewhat close to the grand unification scale. So the one possible answer to the question that the seesaw mechanism would raise is SO10. And in fact, historically, the seesaw mechanism was invented by people that were studying SO10, or at least some people that were studying SO10. Gell-Mann, Slansky, those people were studying SO10, and they, as a byproduct, they invented the seesaw mechanism, although they weren't the first. Minkowski was the first. He did it 2 years earlier, and he didn't use SO10.
Sorry, Steve, you said seesaw mechanism is the most popular mechanism for producing neutrino masses, but in a few slides back, it was at the very bottom of the list of the things that you have to go through.
That's only because the logical order of this is things that can be discovered at the LHC.
Oh, I see.
So if you don't discover anything at the LHC, then you're still left with seesaw models. That was it. It doesn't mean to say that it's not as most important. And I mean, it's a kind of sociological comment I made that it's the most popular, but somebody would have to do the survey. I'm suspecting it's the most popular. All right, so seesaw mechanism. Somebody drew this diagram. An artist drew this diagram for me. So I thought that was quite nice. Yeah, it is.
So what is happening in the middle? That's
so here you've got the observable left-handed neutrinos. You've got the right-handed neutrino in the middle, which she called the mysterious heavy neutrino.
Are they trying to hold on, the left-handed neutrinos? Are they trying to hold on to the heavy middle guy, or?
Well, the way she's drawn it, she's kind of draw them as interacting in some way
That's an interaction
via these Higgses. You see, the Higgs is the giver of mass, so she's drawn it as a little bird here holding a heavy weight.
Mhm. Yeah, that's
Okay.
beautiful.
It is nice.
Yeah.
All right, so now I'm going to very, very quickly, because yeah, otherwise this might break your world record for seminars. So we're going to go through the seesaw mechanism. There's actually two. This was the type 1, which we just talked about, type 1 mechanism, which I'm going to call type 1A, because very, very recently, there has been another version of the seesaw mechanism, which is very, very similar, but involves, instead of involving the same Higgs doublet, HU, you can do a similar thing with two different Higgs doublets, HU and HD. And this is what we call the type 1B seesaw mechanism. So it's a slightly different version. It gives you some new possibilities of testability, because now you've got two independent Yukawa couplings here. So one of them could be rather large, and this could be very helpful for discovering something at the LHC. But I don't have, that's a whole seminar in itself. But
you definitely need two Higgs doublets for this, whereas
you
for
definitely,
the first,
yeah, for this one you definitely need two Higgs doublets. Yeah.
Mhm.
Okay, so then there's the type 2 seesaw mechanism, where you have a different channel. This is the T-channel exchange of a heavy guy, which is now not a right-handed neutrino, it's a heavy triplet.
Mhm.
But it's similar kind of thing, you're exchanging something heavy. And then you've got the type 3 seesaw mechanism, where you have, it's a bit like the type 1, except that you have an SU2 triplet being exchanged, not a sterile neutrino. This is now a fermion, which is an SU2 triplet. Other than that, it's similar to the type 1. Okay, but it doesn't stop.
Sorry, a fermion that is SU2 triplet, that's not, I was going to say, does it have anything to do with the heavy fermions in a Froggatt-Nielsen situation? But
well, yeah, Froggatt-Nielsen is an interesting one. I don't have any time to talk about Froggatt-Nielsen, but Froggatt-Nielsen is basically a copy of the type 1 seesaw mechanism. But yes, you're right. You're exchanging things which are not singlets. So yeah, this. Oh, I see what you mean now. Yeah. This sort of reminds you a bit of Froggatt-Nielsen. Yeah, it's true. Yeah, Colin Froggatt told me that he was inspired when he wrote the paper. They were inspired by the seesaw mechanism, so they just wanted to copy the seesaw mechanism and use it for all fermion masses. Okay, but it doesn't stop there. You've got other extended seesaw models, inverse seesaw and linear seesaw, where these involve adding an extra singlet here, not just a right-handed neutrino, but another singlet, which is in this position, and you get more complicated matrices. But I'm not going to get into that. But that's, you see these words in the literature: inverse seesaw, linear seesaw. Right. Now this slide actually harks back to some discussion we had a couple of hours ago now about the mass of the right-handed neutrinos. What I've done here, just for fun, is I've used the seesaw formula here. M nu is m Dirac squared over m right. I fixed the neutrino mass to be 0.1, and I've plotted m Dirac squared against m right. So that's what you see here. M Dirac squared is on the y-axis, and m right is on the x-axis. And I've, just for fun, I've plotted all the different right-handed neutrino masses. And this might actually clarify this sterile notation discussion that we've been having on a couple of occasions, because here the right-handed neutrino mass goes anywhere from the gut scale, 10 to the 15 or even above GeV, right down here to 1 electron volt. So this is a huge logarithmic scale here. Down here we've got EV sterile neutrinos down here, and up here we've got gut mass sterile neutrinos. Here we've got TeV mass sterile neutrinos. Well, here, yeah, LHC, this is TeV, sorry, this is TeV mass sterile neutrinos here, which is things you can see at the LHC. Here we've got GeV mass sterile neutrinos. Here we've got KV mass sterile neutrinos. And these letters mean something. LSND is the experiment now discredited that discovered EV sterile neutrinos. This WDM means if you've got KV sterile neutrinos, you could use them as dark matter candidates. GV sterile neutrinos is what you have in the new MS minimal standard model, the new standard model. This is the Shaposhnikov version, where they like GV sterile neutrinos. Here's the TeV sterile neutrinos, which LHC enthusiasts like. And here's the gut scale sterile neutrinos, which model builders, grand unified model builders like. Here, just for fun, I've plotted the quark and lepton masses. These colored dots here are the Dirac masses of quarks and leptons. So this is the range. If you want to explain quark and lepton masses, these are the typical Dirac masses of quarks and leptons. So this might give a guide as to what would be a reasonable expectation for the right-handed neutrino masses.
What is the color coding?
That's the three green ones are the charged leptons, E, mu, and tau. The red is the up mass, charm mass, and top mass, which is the heaviest. And the blue is the down, strange, and bottom masses. So they're the quark and lepton masses that we know.
So
there we are.
It looks like a straight line, except that there's a bit of curvature towards the origin. Is there some reason that you?
Well spotted, Denjo. Yes, I did this. I made this plot myself, and I didn't use this formula. I used the exact formula. This is just an approximate formula. If you use the exact formula, this formula breaks down when you have very light right-handed neutrinos. And you have to actually use a more exact formula. And that's responsible for that. You've got sharp eyes, I tell you. That's responsible for this little kink here, because I use the precise formula, not just the approximate formula. So I diagonalized the 2x2 matrix precisely. If you diagonalize the 2x2, it's not difficult. You diagonalize the 2x2 matrix. One of the eigenstates is not just this, it involves the square root of some other masses. And I used the exact formula when I did the plot. And yeah, you can see that you've got a little curvature here. That's right.
Sorry, I still have a question.
You made it worthwhile.
Yeah.
You made it worthwhile, Denjo, that I did the plot exactly, because you're the first person that's ever spotted that. Sorry, Venus, you were saying.
I'm still a little bit confused as to what's these colorful dots are supposed to be telling us. So yeah, what does this mean? I mean, does that mean for me to be using the top quark mass to explain the neutrino mass, I would need a right-handed neutrino around what I find on the horizontal axis?
Exactly. Exactly. So the question is, when you use the seesaw formula, the question is, what mass do you put in for the Dirac mass for the neutrino? And we don't know. We don't know what to put in for the Dirac mass. But you could say, some authors would say that it would be reasonable to put the top mass in to get the neutrino. If you put the top mass in, then that would fix you to this red dot here. So then you would read off the right-handed neutrino would have to be 10 to the 15. And that would be the top mass. It's actually squared because you get a linear relation if you square it. But, and that's the meaning of it. If you say the Dirac mass of the neutrino is equal to the electron mass, then that would mean that that would put you down here with the right-handed neutrino in the sub-TeV region. So it depends what you choose for your Dirac mass for your neutrino. So that's why I plotted the
beautiful plot. Yeah.
Yeah, I was quite proud of it. I did it. Yeah.
I've been taking screenshots of your slides, and my desktop is just completely filled. You do have to share your slide with us here.
I hope you share your slides, because we would.
I'd be delighted to share my slides. Yeah. So
Yes.
I'll probably give you. It's too big to send, so I will make a Dropbox.
That's fine. Whatever way you get them to us is no problem.
Yeah. Certainly, you're welcome. Yeah.
Okay. Appreciate that.
No problem. Okay. So now I think we are approaching some kind of end. I think.
It's getting very late in Beijing.
I don't know how many people are still in the call. Actually, it's gone down to 5. I see. Okay,
yeah.
Well, only the real troopers are left now. So.
But I mean, this is such an interesting story. I want to see how it ends.
Yeah. Okay. Great.
Yeah.
So, all right. So this is a real life example. Well, a full example of the 3x3 example of type 1A. So I mean, this is only 2x2. So, but then the true seesaw mechanism should involve 3 families of neutrinos, and maybe 3 right-handed neutrinos as well. And here you can ask yourself, if you work in a basis where the right-handed neutrinos are diagonal, and you allow the Dirac matrix to be anything you want. This is A, B, C, D, F, A prime, B prime, C prime, and I've put a little primed here for reasons which will become apparent shortly. And then you just put it into the seesaw formula. This is the seesaw formula, m to the -1, m transpose. This is a matrix equation, and this formula gives you the light effective left-handed Majorana neutrino mass matrix, which is this. If you just crank this formula out, it's not that difficult because it's diagonal. You can just multiply these 3 matrices together. You can invert this, multiply these 3. You'll end up with something like this. So each element of the 3x3 matrix has 3 contributions. You can see one from each right-handed neutrino, one from X prime, mass, these are the masses, one from X, one from Y. So each element has 3 contributions. Now, it's very difficult to interpret what's going on. So one simple assumption is called sequential dominance. And that assumption is, first of all, you say that D is equal to 0. So you have a 0 there. And then you say that the red terms dominate. So you say that one of the right-handed neutrinos plays the dominant role in the seesaw mechanism. So this matrix is dominated by the red terms. In other words, this little block here is dominating E squared over Y, EF of Y, F squared over Y. That's called sequential dominance. And that actually gives you some very, very simple analytic formulas for neutrino mixing angles, which means that you can make sense of this matrix in terms of neutrino mixing angles. So that I like. It's also technically natural. I don't like to use the word fine tuning because immediately people jump on me if I say fine tuning, but it's certainly a very reasonable thing to do, is to assume one of the neutrinos dominates. In that case, you get no cancel. These elements don't depend on cancellations. That's the way to say it.
So how is this different from what you were showing on the previous slide, where you said, this is a 2x2 matrix, but now in real life, let's have a 3x3 matrix?
So here I'm just assuming one left-handed neutrino and one right-handed neutrino to make this plot. So this M right is a world where you only have one right-handed neutrino. So this is the real world where you have 3. Well,
but
this is a model where you have 3 right-handed neutrinos, and then it's just life's more complicated with 3 right-handed neutrinos.
Yeah, but most of the job is being done by only one of them.
Exactly. So that's the dominance assumption. Yeah, but most of the job is being done by one. Okay. So that's actually this is my all-time favorite mechanism for neutrino mass. So I would love it if people were interested in that, but unfortunately I don't have time to say much more about it. The point I want to make next is that you can do the whole job of neutrino phenomenology with just 2 right-handed neutrinos. It's still viable. So we could drop the prime terms completely. That means crossing out this one here, cross out that one there. So you could just have 2 right-handed neutrinos. And this is completely consistent with data. And it would actually predict a massless physical neutrinos. So this was proposed a long time ago, but it's still consistent with data. And also, since we have time, I don't normally have time to make these little subtle observations, but if the neutrino mass is 0, then you're right, you have a normal hierarchy. So this sequential dominance predicts a normal hierarchy. So you have to be in this band here somewhere. But the neutrinoless double beta decay cannot be 0, because if this M0, which is really the lightest neutrino mass, if that's really 0, well, it's on a log scale, so you can't. But if it's very, very small, it's the neutrino's double beta decay has to lie in this band. It cannot be 0. So you will see it. You will see neutrino's double beta decay, even though you have a normal hierarchy. You avoid this kind of black hole here where you fall into, and this thing can go down to 0. If one of the neutrino masses is 0, you will see something in neutrino's double beta decay if you have the strength to build the experiment, which can reach this band here. So it will be observable sometime in the future. That's just a little point I like to make.
So how does that relate to the sequential dominance?
Oh yeah, so this is an extreme example of sequential dominance, because here sequential dominance is actually saying that the prime terms are subdominant. So it says in the small print here, it says the red terms are dominant, the prime terms are completely subdominant. But you can actually go to the extreme case where they're so subdominant that you just forget them altogether.
Yeah.
If they're so subdominant, you forget the prime terms altogether. That's like just having 2 right-handed neutrinos. So it's a limit of sequential dominance.
Perfect. Yeah.
And just when you're on this slide, what was the color coding meant to be with the mauve neutrinos? No, the next slide. You've shown it a few times here. You've got the tau R and the nu mu L.
Oh gosh,
yeah.
you've got sharp eyes, Denja.
Yeah.
This is just actually that's supposed to be white. When I made this, I don't know why it came out mauve. I didn't put it in as mauve.
Okay.
That's
sorry.
So I did make this plot myself. But it's not supposed to be mauve. It's supposed to be white.
Because the left-handed muon neutrino is also.
Yeah, I know. Yeah. So I was trying to get the shading, and I think I messed up somehow. And so please pretend that this is the same as these other.
That's fine. I was just wondering what the comment was behind it. But that's all.
This just proves I'm not a professional. Whatever you call it, somebody that makes professional figures. I'm not that person. These are very homemade ones. Yeah, it's supposed to be white. Okay, so we're almost there. The final topic I want to talk about is called littlest seesaw, which is the ultimate in 2 right-handed neutrino models, the most minimal predictive model you can possibly imagine. This is where you have, not only do you have 2 right-handed neutrinos, and not only do you have a 0 here, but then the other couplings are not free, they're constrained. So this coupling and this coupling are the same. These are the couplings to the atmospheric neutrino. And these couplings here are the same, except this one is given a factor of 3. Now, most people really don't like this, because they say, well, this is extremely ad hoc. And why do you assume these are constrained? Maybe you could assume these are equal by some discrete symmetry, but what's the origin of this factor of 3 here? And that's a valid thing to say. The only thing I would say is that you can write down a vacuum alignment that does give you this factor of 3, 1, 3, 1. You can do that and it is possible to make a vacuum alignment. It does it. The other thing I want to mention, and I didn't prepare a slide on it because I thought it would be too much, would be that you can actually use modular symmetry to fix these numbers. And in modular symmetry, you don't actually get a factor of 3, but you get a factor close to 3, it turns out. So you get something very, very similar in modular symmetry, not identical for this factor of 3, but something very, very similar. So, but the message, I think the key message is that you can get these structures from modular symmetry. And we have a paper on that, but it's just that I don't have time to talk about it. So what I'm going to talk about is this older model written before modular symmetry, or written before I worked on modular symmetry, where you have this 1-3-1 structure here. Anyway, the point is that this is an extremely constrained structure. You only have 4 parameters here: A, B, M atmospheric, and M solar, and you can fit these parameters against the data. The data being the 3 neutrino masses, 3 mixing angles, the Dirac CP phase. Well, you don't know what that is, but 2 Majorana phases, we don't know what those are. Also, we did leptogenesis. We fit leptogenesis, so you get 10 observables. So these 4 parameters can explain 10 observables, but only 7 are measured. So the ones we actually used to constrain the fit were θ12, θ13, θ23, the 2 delta m squared. Delta, which we, for this fit, we fixed it between minus 90. Sorry, we didn't fix the delta. The delta is coming out as a prediction, because we've also fixed this phase here, this π/3 phase, which can also be fixed by modular symmetry as well. That actually fixes the delta. So this is a prediction. This is a prediction. But the 7 observables which you can compare to data are these 7 here. Okay, delta is not. We didn't fit that. That comes out as a prediction. What we've fitted to do the fit, we did a chi-squared fit here. This was with 2 students, Malina Sedgwick and she's still in the postdoc market. She's in Valencia, and Sam Rowley, who's left the field. So we did this bit. Yeah, he's left, unfortunately.
Okay.
But Malina Sedgwick, Susanna Malina Sedgwick, is still in the field. Anyway, so we did this bit.
Is this equivalent to having 3 neutrinos and just taking one of them to have essentially MR being infinity?
Yes.
So it decouples completely?
It's completely equivalent.
So it's an approximation for one of them being much larger than the other 2.
You could say, yeah, that's a good way to look at it. You could say it's an approximation to sequential dominance. Yeah, exactly. All right, so we fitted the parameters. You see the A and the B are fitted, and the M atmospheric and the M solar. So these are fitted mainly by leptogenesis, but also by data, by the mixing angles, and these are fitted. And these are the best fits. And these are the predictions of the model. So we predict these mixing angles. You see, we predict the atmospheric angle to be 45 degrees to very high accuracy. So if they ever measure it and if they ever prove it's different from 45, then this model will be excluded. The delta is predicted to be very accurately in this range here. And it also predicts normal ordering and M1 equals 0, like we said. Well, all 2 right-handed neutrino models predict M1 equals 0. But this is I rather like this analysis because it shows what can be possible in terms of predictions. And the miracle, or not miracle, it's not a miracle, it's a fortuitous thing, is that this structure actually explains a lot of parameters, a lot of data with only 4 parameters. All right, we've arrived at the promised land, the conclusions. So this is fantastic, actually. This will be the longest seminar I think I've ever given.
Almost 3 hours.
This will be almost 3 hours.
And I haven't asked 2 of my questions.
Oh my gosh, okay. Well, you still have time for the question session at the end. All right, so here's the conclusions in brief. Well, most parameters are well measured in oscillation experiments, but CP phase, not well measured at all. Could even be, can't be 0, I think, at 3 sigma, but it can be 180. So you can have 180 is equivalent to having no CP violation.
Mm.
That's still possible. The octant, we don't know whether theta 2,3 is less than 45, greater than 45. We don't know the ordering, normal or cyclic. We also don't know whether neutrinos are Majorana or Dirac. We have no idea. And we don't know what the absolute neutrino mass scale is, although we do have the cosmological and laboratory limits. We saw that the tri-bimaximal mixing was explained or enforced by symmetry, which is we like, as physicists, we like things being enforced by symmetries, not just ad hoc, and S4. However, unfortunately, it's excluded by the theta 1,3 measurement, but S4 violations, remember we were violating one or more of the generators. These allow charge lepton corrections or possibly TM1 or TM2 with testable relationships. And remember TM1 and TM2 and charge lepton corrections, again, can all be enforced by symmetries or relaxing symmetries. The origin of Plato's symmetry, we touched on, in other words, the origin of A4 or S4, and is modular symmetry the true origin of these flavor symmetries, which are underpinning possible structures in the neutrino sector? So then that would be a really nice connection between neutrino physics and string theory.
So Plato was a string theorist.
Plato was a closet string theorist,
Yeah.
that's right. He had a lot of secrets, so this might have been one of them. So. And finally, I'm afraid after 3 hours, we still have to admit to ourselves that the origin of neutrino mass is unknown. We still don't know the origin of neutrino mass. All I've done is talk about a few possibilities. And I would say, like I mentioned, theoretical prejudice actually favors the type 1A seesaw mechanism, but in the end, physics is an experimental science and experiment will decide. But I have to say, if it's the high scale seesaw, that's going to be awfully hard to test experimentally.
Well, thank you very much for a fascinating tour through neutrino physics.
Thank you.
Much appreciated. I think we probably owe you a few pints of Guinness.
Yeah. Oh, I'd love to take you up on that, Genjo.
Please join us sometime here in Dublin.
Thank you. I would love to do that. Yeah.
I'm sure Venus will be able to arrange some.
Oh, absolutely. Yeah. I've got an apartment with a guest room.
Anyway, there are still pressing questions that need to be asked. So I think Venus is going to continue for a minute.
Yeah.
Okay.
Yeah. First of all, thank you so much. This was absolutely fantastic. I mean, I don't think I'd ever learned this much in 3 hours in my life.
Okay. Good. I'm glad it was useful.
Good. So the first question I want to ask is actually, about this CP phase. So this is something that would have some benefit to us, right? Can we do some kind of baryogenesis with it? I guess this is what you did with leptogenesis.
Yeah, that's a great question. Thank you. So I like to look at this slide. So this slide, and then I'll come on to the general seesaw. This is not a general seesaw. This is a kind of minimal seesaw with the smallest number of parameters. This has only one input phase. The only input phase is this phase here, this pi/3 phase. So this pi/3 phase is ultimately responsible not only for the CP phase, which is this delta, but it has to be responsible for all phases. It has to be responsible for the Majorana phases, and it has to be responsible for the leptogenesis phase, because it's the only input phase.
Yeah.
So in this model, at least, there is a common origin of all phases. And so by this means, you can get a link between the leptogenesis phase and the phase delta that you measure in neutrino oscillation experiments.
Mm-hmm.
Okay, so this is an example, but there are other models as well on the market that can also give connections between the leptogenesis phase and the oscillation phase. So in general, there's no direct link, and it is possible to have leptogenesis arising just from Majorana phases, and this phase being 0 or 180 degrees.
Mm-hmm.
However, I have to say it's strong circumstantial evidence that if you have CP violation measurable in experiments, then in general, you would feel that there should be some connection with CP violation in the universe. And I haven't said it yet, but obviously CP violation is one of the Sakharov conditions,
of course,
for baryon asymmetry. So I think the what's the word? It's circumstantial evidence. So if you measure the oscillation, CP violation in oscillations, then that would be circumstantial evidence for possible CP violation in the early universe.
Yeah. Perfect. Then a couple of irritating questions. When you're talking about different seesaw mechanisms, you also mentioned, well, one of them was called the inverse seesaw mechanism, and I couldn't tell what was it the inverse of.
Yeah, I don't know why it's called inverse. I guess the clue might be this kind of structure here. I'm not actually sure what the nomenclature.
Isn't it just comparison with the quark sector?
Yeah.
The normal hierarchy is sort of the same order as the quark sector, and what they call the inverse is kind of a different order to the quark sector. Is that not where it comes from?
Maybe, yeah. I mean, the only thing I would say,
came from.
Yeah, could be. The only thing I would say.
And 1, 2, 3 order of the normal sector is the same order as the quark sector.
Okay. The only comment I would make is that the neutrino mass is controlled by this mu.
Yeah.
This is the mass of the singlet. So if you set this mass to 0, then the neutrino masses vanish.
Yeah.
So the whole of the neutrino mass is governed really by this value of this mu. So indeed, these M Dirac masses could be of order the quark masses. That's certainly possible. Yeah.
Perfect. Okay. Then here's another irritating question. If you could go back a lot on the very first slide that you showed that basically proved neutrino oscillation.
What are slides?
Yeah, I think it was a couple of slides
the very
before. That one.
This one? This one?
No. A few slides further down. That one.
This one?
That one, exactly. Yeah. Is there anything special going on around 10 to 2 L/E? Or is that just a statistical fluctuation?
Oh, it looks like statistical, Venus. Yeah, this looks like just statistics at work, I think.
See.
Yeah. I mean, in the real world, you would.
Of course. Yeah, you wouldn't read much into it. So.
Yeah, I wouldn't. Yeah. So yeah, it's 1.5 sigma away or something.
Yeah, and I mean, obviously, if nobody has read too much into it by now, and there's definitely nothing there.
Yeah, there's another one here. There's another one here at the end as well, which is.
And in the very beginning.
Yeah, and these ones, these are even more.
Yeah.
These are even more
you're right.
away.
Yeah.
But yeah, this is probably just statistics at work. I'm guessing.
Yeah.
It looks very like statistics. I mean, you expect with standard deviations like that, you expect to get up to 3. It would not be unusual.
Yeah.
And something as
like
something in like a ratio anyway.
Right. one last question that you mentioned in the beginning, that neutrinos could have something to say about dark energy, but I guess it was just scale-wise you were comparing them, right?
It was just simply, yeah, so it was just simply this observation. And there's been a stream of papers on this, actually, which I've not really been following, but what's the name of this German physicist that's worked on this a lot in the early days? I can't remember his name. Yeah, so there's quite a long history of this, people trying to make this connection between this. It looks like a little bit of a coincidence that this
It's not totally unnatural that the cosmological constant might be related to the slightest particle to the fourth power, that mass. That's one could imagine that there was some mechanism behind that.
Yeah. So yeah, certainly there is a literature on this for sure. Yeah.
Perfect. Yeah.
Yeah.
I think I've asked all of my questions.
Okay, well, thank you for. Obviously, you paid attention, so that's.
I'm going to stop the recording.
I've got a couple of questions.
Oh, go ahead. Continue, Brian, please.
I've got a couple of questions. The S4 symmetry in the lepton sector that you're proposing, I'm not aware of any equivalent discrete symmetry in the quark sector for the CKM matrix. It would seem a bit unnatural or unbalanced to have it on one side but not the other.
You're right.
Yeah.
Is there anything to say about that?
Yes.
Yeah.
Yes. I mean, it's a very, very good point. You can't. So, yeah. Where are we? Yeah. Yeah. Let's just look at this. Yeah. Indeed, these discrete symmetries are really useless for the quark sector. So they're really only good when you're trying to explain large mixing angles. So I mean, if you just think about the tri-bimaximal matrix, okay, you're looking for something with the threefold symmetry here, like a Z3 and a Z2. So you don't get anything like this in the quark sector. So these discrete symmetries are really useless for the quark sector. So my take on this is that to get some handle on the quark masses, you really need to look at grand unification. So the models that I like probably best of all are grand unified models based on SO10 or SU5, which link the leptons and the quarks together. So what I like to do is to combine these discrete symmetries. So these symmetries here, any one of these, I like to combine with a gut group. So for example, you could have A4 cross SU5, or S4 cross SU5, or S4 cross SO10. So where the role of the discrete symmetries is mainly to account for the large lepton mixing, but because it's a grand unified theory, you get a linkage. You get a linkage between the leptons and the quarks. So the quarks are actually also governed by these discrete symmetries, but because the quarks don't have a seesaw mechanism, their masses, what these symmetries are really doing is controlling the Yukawa matrices of the quarks. Now, unfortunately, I don't have an example, but it is possible to combine these symmetries with structures in the quark Yukawa matrices. So they're not inconsistent with quark Yukawa matrices, but
the fundamental differences in the fundamental difference is in the neutrino sector you can have Majorana masses. In the quark sector you can't.
Right, exactly, and that difference is going to be responsible for why the quarks are behaving very differently to the leptons. Yeah, exactly. or to the neutrinos, I should
Thanks.
say.
And I have another question, which I think is probably a little bit flippant. I mean, everyone says that the only way you can have neutrino oscillations is if neutrinos have mass, and clearly it's by far the simplest and probably the correct explanation. But is there actually a mathematical theorem saying there's no other way of doing it? Or is it just that no one has ever thought of another way of doing it, and it's a folk theorem?
Well, thank you for that. Thank you for that, Brian. I was a bit quick when I said that, so let me go back, because I lived through this. I'm old enough to have lived through this. So when I'll tell you a little bit about the history. When this was first discovered, when Super Kamiokande first discovered neutrino oscillations, many people, not everybody said, oh, this has to be a neutrino mass. There were many people that proposed alternative scenarios which didn't depend on neutrino mass. So people were looking at things like decaying neutrinos. They were looking at things like non-standard interactions, like operators, different non-renormalizable operators that you could write down for neutrinos. And they tried many different alternatives, which didn't rely on neutrino mass. So these were thoroughly explored. There's a whole literature on this. And I think Josie Valley was one of the people that really pushed these alternative explanations. And one by one, they were studied by the experimentalists and excluded over the years. And it took several years to test each of these hypotheses. But now it's been shown not mathematically, but experimentally, it's been shown that non-standard interactions, for example, or neutrino magnetic moment operators, these things, one by one, it's been shown that none of them can explain the Super Kamiokande data. So they've studied them. The experimentalists took all these alternative explanations very, very seriously, studied them one by one, and ruled them out one by one. So now I think the current status is that the only possible explanation is neutrino mass, which I think was after that point was arrived. I think that's when they awarded the Nobel Prize.
Yeah.
So perhaps a more correct statement is that the only viable explanation is a mass.
Mm.
And it's not.
Yeah, correct.
The only possible explanation of mass is perhaps a little extreme, but.
Yeah. Okay. Yeah.
Sorry, I'm being pedantic.
So,
no, I understand.
No.
Yeah.
Yeah.
It's
So
awaiting your suggestion, Brian, for an alternative.
Yeah. I mean, the door's still open, of course. Yeah. In principle, some person could come up with a new explanation that nobody's thought of. That's your point. Yeah.
Right.
Yeah. Absolutely. But physics is always like that.
Yeah. Sure.
Well, my own bet would be that the masses are almost certainly the right explanation. Just when you don't work in a field and people who work in the field say that something is impossible, you never really know if it's impossible or if it's
of course, there's no such word in physics as impossible. Yeah. Absolutely.
Okay. I'm going to stop the recording if that's okay. And any other questions are going to be lost to the ether.
Yeah, I just wanted to say a comment. Talking about people